Welcome back for another deep dive, everyone. You guys have given us quite a paper this time.
Oh, yeah.
It's called Siegel Vectors for Nongeneric Depth, 0 Supercuspidals of GSp4.
It's a mouthful.
It is.
Yeah.
It is. And it looks like we're going to be exploring some pretty advanced representation theory.
Definitely. And there are even some connections to classic number theory problems in here.
Oh, very cool. Very cool. So I guess to get started, maybe you could give us a little bit of context. Like, what's the main idea behind this paper? What problem are the authors trying to solve?
Sure. So at its heart, the paper is really about calculating dimensions, certain dimensions.
Yeah.
You know, how big are certain spaces? And these are spaces of special vectors, what are called fixed vectors, that are like unchanged when you hit them with certain group actions.
I see.
And these calculations, as you mentioned, they actually have some really cool connections to understanding dimensions in the classical theory of Siegel modular forms.
Oh, wow. Okay. Could you maybe give an example of that? Like, how do these fixed vectors relate to Siegel modular forms?
Yeah, so a great example is when you look at dimension calculations for spaces of cusp forms,
Right.
for Klingon congruence subgroups.
Mhm.
To do that, you really need to know the dimensions of certain fixed vectors in representations of GSp4 Q2.
Oh, that's fascinating.
Yeah.
So to understand these classical objects, we need to delve into the world of representation theory.
Exactly. It's like these two seemingly different areas are actually deeply interconnected.
I love that. And before we go any further, I just want to be clear with our listeners. We are diving deep here, so we're assuming you're already familiar with the basics of p-adic representation theory.
Right. We won't be reviewing like group theory 101.
Exactly. Now, you mentioned something intriguing earlier about a surprise the authors uncovered.
Mhm.
Something about prime numbers.
Oh, yeah. That's one of the really fascinating things about this paper.
Okay.
They find this surprising difference in how these dimensions we're talking about. They behave depending on whether you're working with the prime number 2 or any other prime number.
Ooh, a prime number plot twist. I'm hooked already.
Haha. Yeah, it's pretty neat.
Okay, well, I'm ready to unpack this. Why don't we start by taking a look at the introduction of the paper?
Sounds good to me.
I imagine it lays out the problem they're trying to solve and maybe gives a sneak peek of their results.
You got it. The introduction really sets the stage by explaining the big picture and summarizing the main findings.
Okay, so what's the big picture? What exactly is the problem they're tackling?
Essentially, they're trying to solve this dimension counting problem in the world of p-adic representation theory.
All right, so we're counting something, but what exactly are we counting?
We're counting how many special vectors we have, what they call Siegel vectors, that stay fixed or invariant under the action of certain subgroups.
Okay, so we're looking for vectors that are like unfazed by these specific group actions.
Exactly. Like they're just chilling there, unmoved by all the group action happening around them.
Got it. And the subgroups in question here are the Siegel congruent subgroups. Right?
You got it.
And they're focusing on a particular kind of representation, right? The depth 0 supercuspidal ones.
Right. They're looking at depth 0 supercuspidal representations of GSp4, but even within those, they narrow their focus.
Oh, even more specific.
Yeah, they zoom in on the non-generic ones, which are built in a particular way involving this subgroup called KP.
So we're really zeroing in on a tiny corner of this mathematical universe.
Pretty much. And what's interesting is that they actually point out in the intro that they're covering all the interesting cases of Siegel vectors for these specific non-generic depth 0 supercuspidals.
All of them.
Yeah, and they even mention that if you look at non-generic representations coming from a different subgroup denoted by K, there are no Siegel vectors at all.
No Siegel vectors at all.
None. So already we're seeing that the specifics of how these representations are built really matter.
It's amazing how much structure there is even within these abstract mathematical objects.
Yeah, it's pretty incredible.
Okay, so the introduction sets the stage by telling us what problem they're solving and what types of representations they're focused on.
Mm-hmm.
Anything else it highlights?
Well, they definitely emphasize this key finding that there's a fundamental difference between the prime number 2 and all other prime numbers.
Right, the prime number mystery. So that distinction plays a central role throughout the paper.
It's a recurring theme, that's for sure.
Okay, well, now I'm even more intrigued. So the introduction has given us the problem statement and hint of the results.
Right.
What's next? I imagine section 2 is probably where they lay out all the mathematical tools they'll be using.
Exactly. Section 2 is like opening up a mathematician's toolbox. It's packed with definitions, notation, all the things we'll need for a deep dive.
Okay, let's take a peek inside this toolbox. What kind of tools are we talking about?
Well, they start with the basics.
Okay.
We've got F, which represents this non-archimedean local field of characteristic 0. Think of it as a generalization of the p-adic numbers.
Okay, so we're working in this p-adic world.
Right. Then we have O, which is the ring of integers of F and P for the maximal ideal, and as a uniformizer, and F sub Q sub for the residue field, all the usual suspects.
Okay, so we're laying the groundwork with our p-adic number system.
Yeah, it's like setting up the playing field.
And they make a specific assumption about this p-adic field, right? Something about when p equals 2.
Right. They assume that if p equals 2, then the extension fq sub 2 sub is unramified.
Okay, so that's a condition that will probably come into play later on.
Oh, yeah. It definitely plays a role.
Okay, so we've got our p-adic field, our ring of integers, and so on. What else is in this mathematical toolbox?
A lot of groups. They define GL sub 2002 sub q, which consists of pairs of matrices from GL sub 2 sub q with equal determinants. Then we've got GSp4 F, the star of the show, so to speak.
Right, the group we're ultimately interested in.
And of course, they define the center of this group, denoted Z, the set of diagonal matrices T, and the subgroup G sub 0 sub consisting of matrices of the form.
Wait, hold on. Even for our expert audience, that's a lot of groups to juggle.
Yeah, you're right.
Maybe we can just say that they define a whole bunch of groups, all related to GSp4F in some way.
Yeah, that's a good way to put it. They're kind of like different subfamilies within the bigger GSp4F family.
I like that analogy. So we've got our groups, and I bet they define even more subgroups of these groups, right?
You bet. They introduce the maximal compact subgroups K and Kp, the standard Iowa-Hori subgroup I, and drumroll please, the Siegel congruent subgroups, Sip sub sub.
There they are. The ones we're ultimately interested in when counting those special Siegel vectors.
Exactly.
Okay, so we've got groups, subgroups. Are we done with the group theory yet?
Almost. They also define something called K sup plus sup, which is the pronipotent radical of Kp, and they point out this important isomorphism between Kpp plus sup and GL sub 2002 sub q.
An isomorphism. So that means these two seemingly different objects are actually the same, just dressed up in different mathematical clothes.
Precisely. And that connection will be really useful later on.
Okay, I'm starting to see how these tools might come in handy. What else is in our toolbox?
Well, we need to talk about representations, right? So they introduce some notation for that, like rhi sub 1 sub here sub 2 sub,
Right.
to represent a certain type of representation built from two smaller representations, sub 1 sub and sub 2 sub.
Hey.
And they use C in tub G sub 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 for something called the compactly induced representation.
Right. Compact induction is like a way of building a bigger representation out of a smaller one.
Exactly.
Okay, so we've got our notation for representations. Anything else?
Oh, yeah. They also introduce some special matrices, sub 1 sub, sub 2 sub, and U sub sub, that will play important roles later on.
Okay, so we've got our groups, our subgroups, our representations, our special matrices.
Yeah.
It's a lot to keep track of.
It is, but think of it like this. We're gearing up for a mathematical expedition, and these are all the essential supplies in our backpack.
I like that. We're mathematical explorers.
Exactly.
Okay, so we're almost ready to set off on our expedition, but first we need to understand the types of representations we'll be encountering on this journey, right?
You're right. Before we dive into the calculations, we need to know what kind of creatures we're dealing with.
Okay. So what can you tell us about these depth 0 supercuspidal representations? How are they built?
Well, the authors explain that they arise in two ways. One way is as a Kc in sub G sub Z K sub, where each is a representation of a subgroup restricted to K.
Yeah.
And the other way is as C in sub G sub sum G, where it is an irreducible representation of the normalizer of Kp in G.
Okay, two different recipes, but they both involve compact induction, right?
Exactly. Compact induction is our key ingredient here. And in that second case, where we have Hc in sub G sub in GKP sub sum in G, the representation when restricted to Kp, can actually take on a couple of different forms.
Oh, so there are variations within that second recipe.
Exactly. It can be either an irreducible representation of Kp sub plus sub, or it can be supersum sub sub, where super sub 1 sub sub is a representation built from as the matrix E sub 1 sub we talked about earlier.
Okay, and when does it take that second, more complicated form?
That second form, super sub 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 sub, pops up only when suz is not equivalent to super sub 1 subs.
So it depends on how us interacts with that special matrix U sub 1 sub.
Exactly. And that distinction, believe it or not, is going to be crucial when we finally get to those dimension calculations.
Okay, well, you've definitely piqued my curiosity.
Yeah. Ha ha.
So we've got our p-adic number system, our groups and subgroups, our notation for representations, and 2 ways to cook up these depth 0 supercuspidal representations. I feel like we're finally ready to set off on our mathematical expedition.
Me too.
What awaits us in Section 3?
Section 3 is where the action really starts. It's all about calculating those dimensions, the dimensions of the spaces of Siegel vectors we've been talking about.
All right, that's the heart of the paper. But before we jump into those calculations, I have a feeling there's some clever formula they use to break down this problem into smaller pieces, right?
I have a good feeling. They introduced this formula for dim sup size sup, which is the dimension of the space of Siegel invariant vectors of level sup, and they express it as a sum over certain double cosets in NGP.
Double cosets, those are always fun. So each term in that sum corresponds to a specific double coset.
Exactly. And each term in the sum gives us the dimension of the space of vectors in sub that are fixed under the action of this subgroup R sub.
R sub, another subgroup.
Yeah, it's defined using the double coset representative GKE.
So in essence, they've taken this big, complicated dimension and broken it down into a sum of smaller, more manageable dimensions.
That's a great way to put it.
But to actually use this formula, we need to figure out 2 things, right?
Mm-hmm.
First, we need to know which double cosets actually contribute to the sum.
Right. Not all of them will matter.
And second, for each double coset that does matter, we need to calculate that smaller dimension, the dimension of sup arXiv.
You nailed it.
And that sounds like it could get pretty complicated.
It definitely can, but the authors have a few tricks up their sleeves.
Well, I can't wait to see what they are.
And that's where the character tables come in.
Oh, okay. Character tables. Those are like cheat sheets for representations, right? They tell you all the important properties.
They do. They're super useful for organizing information about representations.
Okay.
And in this case, they use these character tables to figure out dim sup for certain subgroups R of GL sub 2002 sub Q.
I see. So they're kind of building up to those R subs by first looking at some simpler subgroups.
Exactly. They start with the building blocks and then put them together.
Okay, so what kinds of subgroups are they looking at in this section?
The key lemma here is lemma 3.2.
Okay.
And it lays out 4 different cases for a sub 1 sub, a sub 2 sub. But in all 4 cases, we're assuming that sub 1 sub and O sub 2 sub are these irreducible cuspidal representations of GL sub 2 sub Q that satisfy this condition. O sub 1 sub 2 sub equals 1.
Okay, so a specific type of representation satisfying a specific condition.
Right, and that condition on the central characters is going to stick around throughout the paper.
I see.
Okay.
Okay, so what does the first case in lemma 3.2 tell us?
So the first case looks at this subgroup R, where the elements are pairs of matrices with a specific form.
Yep.
And the lemma tells us that in this case, the dimension, dim sup cup, well, it depends on whether Q is even or odd.
Oh, of course. Even and odd, that seems to be a recurring theme here.
Right. If Q is odd, the dimension is 1 plus sup co 1. But if Q is even, it's just 1.
Okay, so even in this simple case, we're seeing that dichotomy between even and odd Q.
Yeah, and notice how the dimension also depends on the representation itself through that ho sub term.
Right, so it's sensitive to both the underlying field and the specific representation we're looking at.
Yeah.
Okay, what about the second case? What does that tell us?
So case 2 focuses on a slightly different subgroup, still with pairs of matrices, but with a slightly different form.
Okay.
And what's interesting is that this case can only happen if Q is odd.
Ah, so already a restriction based on the field.
Right. And if Q is odd, the dimension is 1 plus O sub y sub 1, 2, which actually works out to be either 1 if Q is congruent to 3 modulo 4, or 0 if Q is congruent to 1 modulo 4.
Wow, so now we're even seeing divisibility by 4 come into play.
Haha, yeah. Number theory is full of surprises.
Okay, 2 cases down, 2 to go. What does case 3 tell us?
Case 3 looks at yet another subgroup.
More matrices?
More matrices, but this time the formula for the dimension is nice and simple.
Oh, good. I could use a break from all those congruences.
Haha, it's just Q1.
Oh, wow, okay. That's refreshingly straightforward.
Right. And then finally we have case 4, which is specifically for even Q.
Of course.
Yeah.
Even Q always gets its own special treatment.
It does. So in this case, the subgroup R is a bit more complicated.
More complicated matrices.
You bet. But the dimension is always just 1.
Okay, so even though the subgroup itself is messy, the dimension is nice and clean.
Exactly.
Okay, so lemma 3.2 has given us a taste of how these dimensions can vary depending on the subgroup R, the field F sub, and the representation.
It's like a preview of the complexities to come.
I'm starting to get a feel for how subtle this all is.
Yeah, it's pretty amazing how much nuance there is here.
So we've calculated dim supersup for those special subgroups. What's the next step?
So remember, our big goal is to figure out which double cosets actually matter in our dimension formula.
Right. We need to find the support of, which is all those double cosets where restricted to R sub is non-zero.
Exactly. That's what section 3.2 is all about, determining sub.
Okay, and how do they go about finding this support?
Well, they use this clever decomposition of the group G.
Another decomposition.
Haha, yep. They write G as a product of the Iwahori subgroup I, the normalizer of the torus NGT, and I, again.
I and GTI. I remember we defined those back in section 2.
Right. So using that decomposition, they can actually focus on double coset representatives that have a very specific form, SUBI J sub SX Y Z.
Okay, let me try to break that down. So SUBI J sub is a diagonal matrix with powers of the uniformizer along the diagonal, right?
That's right.
And SXYZ is, well, it's a specific type of matrix with entries X, Y, and Z in the maximal ideal P.
You got it.
Okay, so we've narrowed down the possibilities for our double coset representatives, but it still seems like a lot of options.
It does, but the authors, they're pretty clever.
I'm sure they are.
They use these subgroups, U sub 1 sub and U sub 2 sub.
Oh, more subgroups.
Yeah, well, these subgroups have a nice structure that allows the authors to impose some restrictions on the valuations of X, Y, and Z.
Valuations, those tell us how divisible an element is by that uniformizer.
Exactly. So by carefully analyzing those valuations and using a series of lemmas, they're able to show that any double coset in the supportive clique can be expressed using the Siegel-Levi subgroup, denoted by M.
The Siegel-Levi subgroup. Okay, I think we've seen that before.
It's one of the many groups we defined back in section 2.
Right. So what exactly does this mean for our double coset representatives?
They proved that if you have a double coset G that's in the support of, then the representative G has to take on one of 4 very specific forms.
Oh, wow. So they've really narrowed it down. What are those 4 forms?
Okay, so the first one is just G epil subi J sub, a nice simple diagonal matrix. The second form is G quote subi J sub 0, 0, 0.
So it's like the first form, but with an extra S matrix tacked on.
Exactly. The third form is G equals subi AJ sub S S Y Z. So again, we have that S matrix.
And the fourth form.
That one's the most complicated. G subi J sub S X Y Z. But there's a catch.
Oh, there's always a catch.
Right. So in this fourth form, the valuation of Z has to be related to the valuations of X and Y in a specific way. And also, if the product legs YZ is non-zero, then Q has to be even. And there's another condition on the valuations.
Okay, so a lot of conditions for that fourth form.
Right. But the point is, we've gone from an infinite number of possibilities for GOG to just 4 specific forms.
That's pretty impressive. They really narrowed it down.
Yeah.
Do they give those 4 forms names?
They do. They call those 4 types of double cosets types. I, E, A, and 4.
Okay, so now we can just refer to them by their types. It's handy.
Yeah, it keeps things organized.
And they even summarize all of this in a table, right? Table 1.
They do. Tables are a mathematician's best friend.
Agreed. So now we know what forms those double cosets can take, but we still need to figure out when each of those forms is actually in the support of.
You're right. We need to go through each of those 4 types and see if they satisfy the conditions for being in the support.
And that sounds like it could get pretty technical.
It does, but luckily, Lemma 3.8 lays out all the necessary and sufficient conditions.
Oh, that's helpful.
Yeah, it's like a checklist for each type of double coset.
So let's start with type I. What conditions do we need to check for that one?
Okay, so type I is the simplest one, just G, GIA, J sub. The lemma tells us that if either Q is even or Q is odd and I has a trivial central character, then we're good, that double coset is definitely in the support.
Okay.
And in that case, R sub TJ sub actually takes on the same form as that subgroup we saw in the first case of lemma 3.2.
Oh, cool. So those character table calculations are starting to come in handy.
They are. Everything is connected.
I love it. What about type 2? What conditions do we need to check for that one?
Okay, so type II is G equals subi J sub X 0, 0. And the lemma says that if the valuation of X is less than or equal to I plus J, then that double coset is in the support if and only if Q is even and the valuation of X is equal to I plus J.
But type 2 is a bit more restrictive.
It is.
We need both Q to be even and a very specific condition on that valuation.
Right.
And in that case, what does R sub T J sub SX 0, 0 look like?
It actually ends up being the same form as that subgroup in the first case of lemma 3.2 again.
Oh, interesting. So even though the double coset representatives are different, the R subgroups can be the same.
Exactly. It's all about how things intersect and interact with each other.
Okay, 2 types down, 2 more to go. What about types I psi I and IIB? Those are the ones where G equals the J sub S 0 YZ, right?
Right. And lemma 3.8 tells us that if the valuation of y is less than or equal to J1, then this double coset is in the support if and only if, again, Q is even, and J minus the valuation of y is less than or equal to 2.
So again, we need Q to be even. And this time, there's a condition on that difference between J and the valuation of y.
Exactly. And depending on whether that difference is 1 or 2, the subgroup R subtype J sub S 0 YZ takes on a specific form, which we won't go into detail about right now.
This is good to me.
Eh.
Let's move on to type IV. That's the most complicated one, right?
It is. So remember, type IV is G plus 1 plus the valuation of y with a specific condition on the valuation of Z.
Right. The valuation of Z has to be 2I plus 1 plus the valuation of Y.
Exactly. So lemma 3.8 tells us that if Q is even, the valuation of y is less than or equal to J1, and I plus the valuation of yx is 0, then that double coset belongs to the support if and only if J minus the valuation of y is equal to 1.
Okay, a lot of conditions to check there.
I know, right?
But it's amazing that they were able to pinpoint exactly when this type of double coset contributes.
It's pretty impressive. They really had to dig into the details.
It's a real testament to their mathematical prowess.
Yeah.
So to sum up, we've now got a complete picture of which double cosets belong to the support of.
We do.
We know what forms those double cosets can take.
Right.
And we know when each of those forms actually shows up.
Exactly.
So what happens next? I'm guessing now that we know which double cosets are relevant, we need to count them.
You guessed it. That's what section 4 is all about.
Okay, because we're trying to calculate a dimension which involves summing over all those double cosets.
Right.
So we need to know how many of each type we have.
Exactly.
And I imagine they have some clever techniques for counting those double cosets.
They do.
Well, I'm ready to hear about them.
Mm-hmm.
So to refresh our memory, what exactly is this Aitken-Leonard involution, and why should we care about it?
Okay, so the Aitken-Leonard involution, usually written as U sub sub, it's this special operator that acts on the space of Siegel invariant vectors. It's kind of like, you know, a reflection or a flip.
Okay.
And it has some interesting properties that make it worth studying.
Okay, I'm kind of picturing it, but I guess I'm still a little fuzzy on why this reflection is so important.
So the key thing is, by understanding how this Aitken-Leonard involution acts on our vectors, we can learn more about the representations themselves.
Okay.
Like we can calculate something called the signature of the involution.
Signature. Okay, I'm intrigued.
Yeah. So the signature basically tells us about the balance between positive and negative eigenvalues of the Aitken-Leonard involution. It's like a way of measuring how much this reflection changes the eigenvectors in our space.
Got it. So it gives us a more refined understanding of what the involution is doing. Okay, so how did the authors approach this Aitken-Leonard involution in this paper? Did they, dive into the nitty-gritty details?
Oh, absolutely. They got right into it, starting by analyzing how the involution acts on those different types of double cosets we talked about earlier, types I through IV.
Right. Those double cosets determine which pieces contribute to our dimension formulas.
Exactly. So they had to figure out how the involution mixes up those double cosets.
Okay, so they looked at how the involution permutes those double cosets.
Yes. And not only that, for each type of double coset, they actually worked out formulas for how the involution transforms the corresponding vectors in the representation space.
So, if you have a vector associated to a certain double coset, they figured out what happens to that vector when you hit it with the Aitken-Leonard involution.
Exactly.
I bet those formulas got pretty hairy.
Oh, yeah. Lemma 6.1, which is where they lay it all out, it's pretty technical.
I can imagine. So it basically describes how the involution acts, case by case, for each type of double coset.
That's a good way to put it.
Can you give me, a quick example of what one of those formulas looks like, just to get a sense of the flavor?
Sure. So for type I double cosets, remember that those are represented by Gi to subi J sub.
Okay.
The formula tells us that we sub F subi to sub subi N to I J sub.
Wow, okay, that's a mouthful. We try to parse that.
that.
So U sub F, that's representing the action of the Aitken-Leonard involution on the function F, right?
Yeah, you got it.
And then we evaluate that at the double coset representative subi J sub on the left side. And on the right side, we have U sub 1 sub FF, which means we're applying that matrix U sub 1 sub to the function,
Right.
and then evaluating that at subi N to I J sub. So it's like The involution shifts things around, not only the function, but also the point where we're evaluating it.
Yeah, it's kind of shuffling things around in a very specific way.
Okay, I think I'm starting to see how this works.
Good. And what's cool is that the lemma also tells us that the double cousets G and go sub are the same if and only if n is odd and equal to 2i plus 2j plus 1.
Interesting. So sometimes the involution actually leaves a double coset fixed.
Exactly. It's not always permuting them.
And it looks like whether it fixes the double coset or not depends on n and those indices I and j.
Right. It's all interconnected.
I love how all these pieces fit together.
Me too. It's very satisfying.
So lemma 6.1 gave us all those formulas for how the Akin-Lehner involution acts. But remember, the big goal was to calculate its signature, right?
We want to know how many pluses and minuses we get when we look at its eigenvalues.
Exactly. And that's where theorem 6.2 comes in, right?
You got it. Theorem 6.2, it gives us the formulas for that signature, denoted Sn, and it splits things up into cases based on whether n is even or odd.
Okay, so two main cases to consider.
Yep.
Let's start with the even case.
What?
What does the theorem tell us when n is even?
Okay, so when n is even and at least 4.
Okay.
If q is odd, the signature is just as 0.
Okay, so a simple answer for odd q.
Right. But if q is even, then the signature is 1 plus qn for 2 times this factor that depends on, you guessed it, the relationship between sus and super sub 1 sub sub.
Oh, of course. That relationship is always popping up. So what are the possible values for that factor?
It can be either 2 if sus is not equal to super sub 1 sub sub, or 1 if they are equal.
Okay, so again, the signature depends not just on n, but also on the specifics of the representation.
Right, it's all connected.
And it looks like there's a big difference between the odd q and even q cases when n is even a signature of 0 versus something potentially non-zero.
Yeah, that's a key observation.
Okay, so the even case has some interesting nuances. What about when n is odd? I bet those formulas get even more intricate.
They do. So first of all, there's this plus or minus sign that appears in the formulas, and it depends on how we choose to extend the representation.
Okay, so a little bit of ambiguity there depending on our choices.
Right, but if q is even, the formula is a bit simpler. It's piecewise, depending on n.
Piecewise, meaning it has different formulas for different ranges of n.
Exactly. So if sus is not equal to super sub 1 sub sub, it's just 0.
Okay.
If n is 3 and it is equal to super sub 1 sub sub, then the signature is 1.
Okay.
And if n is at least 5 and sus is equal to super sub 1 sub sub, then the signature is 1 plus q and 4.
Got it. So those smaller values of n, they often have their own special cases.
It's a pattern we see a lot in number theory.
Okay, and what about if q is odd? Does the signature get even more complicated?
Well, it does involve a few more conditions.
Okay.
So if q is odd, the signature is plus or minus n1 2 times a factor, and this time the factor depends not just on whether supo equals super sub 1 sub sub, but also on whether it's of the form ara.
Okay.
And if it is of that form, then it also depends on whether super sub equals 1 or this non-trivial quadratic characterless sub 0 sub.
Wow, okay, so a lot to unpack there.
Yeah, there are a few different subcases to consider, but the theorem lays it all out very carefully.
So even though the formula itself is complicated, it's like we have a roadmap for calculating the signature in any situation.
Exactly.
And I'm starting to see a theme here. The signature formulas are really sensitive to the specific form of the representation and its relationship with super sub 1 sub sub.
That's a great observation. It makes sense because remember, the Akin-Lehner involution is itself a reflection.
Right.
So its signature is going to tell us how that reflection interacts with the symmetries that are built into the representation.
That's a beautiful way to think about it. It's like the signature is capturing the interplay between these different mathematical structures.
Exactly. It's all about how things fit together.
And I love how the authors gave us that concrete example in Corollary 6.3, where they present the signatures for the specific case of f is q sub 2 sub.
Oh, yeah, that example is really helpful for seeing how these abstract formulas actually play out in practice.
Totally. And they even point out that there are two different extensions, tus sup, plus sup, and psi pru sup, which lead to two different representations, sup plus sup, and sub per sup.
Right, so even in this specific case, we still have some choices to make, and those choices affect the final answer.
It's amazing how much complexity can arise even in seemingly simple situations.
It really highlights the power and the beauty of mathematics.
Okay, well, I feel like we've been on quite a mathematical adventure here.
Oh, we have.
We've explored dimensions, signatures, the Akin-Lehner involution. It's been a whirlwind tour through the world of p-adic representation theory.
It has been a lot of fun, though.
Absolutely. So maybe as a final thought for our listeners, we could try to sum up the key takeaways from this paper. What are the big ideas they should walk away with?
Well, the main accomplishment of this paper is that it solves this very specific but important problem,
Okay.
calculating the dimension of spaces of Siegel vectors for these non-generic depth zero supercuspidal representations of GSp4.
Right.
And they did it by carefully analyzing which double cosets contribute to the dimension formula, counting those double cosets, and then working out explicit formulas for the dimensions.
And those formulas, they depend on all sorts of things, right? The prime number p, the size of the residue field, the specific structure of the representation.
It's all interconnected.
And they didn't stop there. They also delved into the action of the Atkin-Lehner involution.
Right. They figured out how it acts on the double cosets, and they derived formulas for its signature.
And those signature formulas, they're equally intricate and sensitive to all those subtle details.
It's amazing how much information is packed into these formulas.
It's like a testament to the power of mathematical thinking,
Absolutely.
how we can use these abstract tools to unravel these incredibly complex structures.
It's like we're peeling back the layers of reality, one mathematical concept at a time.
I love that analogy. And as the authors point out, this work could potentially have implications beyond GSp4.
Oh, yeah. The techniques they developed here could potentially be applied to study other groups as well.
So it's like they've opened up a whole new avenue of research.
Right. And who knows what other mathematical treasures are out there just waiting to be discovered.
Well, on that exciting note, I think it's time to wrap up this deep dive. I want to thank you so much for being our guide on this mathematical journey.
It was my pleasure. Always happy to talk about math.
And to our listeners, thank you for joining us on this adventure into the world of Siegel vectors, c-adic representation theory, and the incredible beauty of abstract mathematics. We hope you've enjoyed the ride, and we'll see you next time for another deep dive. All right, let's dive deep into some p-adic representation theory today.
That's good.
We're taking a look at Jonathan Cohen's paper, Siegel vectors for non-generic depth, zero supercuspidals of GSp4.
Yeah, it's quite a paper. Lots to unpack there.
Definitely. So for our listeners, Siegel modular forms, they have these really interesting properties.
Right, and they pop up all over number theory.
Exactly. But one thing that's been tricky for mathematicians is figuring out the dimensions of the spaces these forms live in, especially when you're dealing with certain types of congruent subgroups.
Yeah, that's a real challenge.
It is. In this paper, it actually tackles this dimension problem for Siegel congruence subgroups of level p to the n.
Yeah, and it focuses specifically on the dimensions related to a certain type of representation. Depth, zero supercuspidal representations coming from the group KP.
Okay, now I've got to ask about this dichotomy between prime numbers that I saw mentioned. What's that all about?
You'll see as we go through the paper that the prime number 2, it acts a bit differently than all the other primes when we're calculating these dimensions.
Interesting. So we've got like a prime suspect, huh?
You could say that.
Okay, I'm hooked already. But let's back up a bit. Can you remind me what a depth zero supercuspidal representation is and why it matters in this context?
Sure. So basically, a depth zero supercuspidal representation, it's a special type of representation. You find it when you're studying p-adic groups. They're like, I guess you could say building blocks for more complicated representations, and they have certain properties that make them really interesting when you're studying Siegel modular forms.
Okay, and why are we zeroing in on the ones that come from PAP?
Well, these representations that originate from KAP, they're crucial for figuring out the dimensions of spaces of Siegel invariant vectors. And remember, Siegel invariant vectors, they're basically vectors that don't change when you apply the action of the Siegel congruent subgroup.
Cool.
So understanding their dimensions gives us important information about the corresponding spaces of Siegel modular forms.
Got it. So these depth zero supercuspidal representations, they're like the keys to unlock the dimensions of these spaces.
That's a good way to put it.
Okay, now how do we actually go about calculating these dimensions?
Well, the paper uses this really neat approach with double cosets in their classification. By breaking down the group GSp4 into these double cosets, we can tackle the problem in smaller, more manageable chunks.
So it's like a divide and conquer strategy, but in the world of math.
Exactly.
I like it. Tell me more about these double cosets and how they're classified.
So a double coset is basically a set you get by multiplying an element from one subgroup on the left and another subgroup on the right. In our case, we're looking at double cosets that have the form NGT, GSp4. NGP is the normalizer of Kp and G. G is an element of GSp4F, and SciPn is the Siegel congruence subgroup of level P to the N.
Okay, so we're taking an element from the normalizer, kind of sandwiching it between an element of the group and an element from the Siegel congruence subgroup, and then we see what we get.
Right, and by analyzing the structure of these double cusps, we can sort them into 5 different types: I, 2, I3, II, and 4.
So each type is like a piece of the puzzle, and once we understand each piece, we can solve the whole thing and figure out the dimension. Can you tell me a little bit more about how these 5 types differ from each other?
Sure. Type I, that's the simplest one. It's just a diagonal matrix. Type 2 is a little more interesting. It only shows up when the size of the residue field, Q, is even.
Okay, so evenness is starting to matter already.
Yes, and it gets even more complex with type 3, which actually has 2 subtypes, I3AI and the IB.
2 subtypes, okay.
Yeah, both of them only exist for even Q, and you need N to be big enough for them to appear. Type 4 also only exists for even Q.
Wow, so whether Q is even or odd, that really seems to make a big difference.
It really does, and you'll see this even more clearly when we look at the actual dimension formulas.
All right, well, I'm ready for those formulas.
Yeah.
How does the paper use these double cosets to actually calculate the dimensions?
It comes down to how the depth zero supercuspidal representation interacts with each type of double coset. The dimension of the space of Siegel invariant vectors, it's calculated by adding up the dimensions of certain subspaces, and each of these subspaces is linked to a specific double coset.
So like we're adding up the contributions from each type of double coset.
Exactly, and the paper gives us formulas to calculate these contributions. These formulas are based on the properties of the representation and the characteristics of each double coset type.
Sounds pretty involved. Can you give me an overview of the main theorem that lays out these dimension formulas?
The heart of the paper is Theorem 5.1. It separates things into 2 cases: when Q is odd and when Q is even. When Q is odd, only type I double cosets contribute to the dimension. But when Q is even, all 5 types play a part, and the formula gets more complicated.
So that's where the prime number 2 comes in, right?
Exactly. The formula for even Q uses this new function, FNQ, and it captures the total contribution from all the double coset types. And this function behaves very differently from the formula for odd Q, showing just how special the prime number 2 is.
This is fascinating. We've got these formulas to get the dimensions of the spaces of Siegel invariant vectors, but the paper goes even further, right? There's something about an Aitken-Lehner involution.
Ah, yes. The Aitken-Lehner involution, it adds another layer of complexity and insight to all of this. Think of it as a special transformation that kind of flips things around in our space.
So it's like a mathematical mirror for our representations. How does it affect the spaces of Siegel invariant vectors?
Well, it turns out it can change the dimensions of these spaces. We look at its signature, which we denote by sum. This signature measures the difference in dimensions between the plus and minus eigenspaces of the involution.
Interesting. So the signature tells us how much the dimensions change when we apply this flip. Does the paper give us formulas for the signature too?
Absolutely. Theorem 6.2 gives us the formulas for S, N, and again, it makes distinctions between even and odd N and even and odd Q. These formulas show just how much the signature depends on the interplay of N, Q, and the specific characteristics of the representation.
Wow, this is getting pretty deep. But before we get into the nitty-gritty details of the proofs, let's make sure we're all on the same page with some definitions. We've been using terms like non-archimedean local field, uniformizer, and residue field. Could you give us a quick refresher on what those mean?
Of course. So F, it represents a non-Archimedean local field of characteristic 0.
Which sounds intimidating, but...
It might sound complicated, but you can think of it as a field with a special way of measuring distance that's different from the usual distance on the real number line. We're also going to assume that FQ2 is unramified if the residual characteristic of F is even. This makes our calculations work out nicely.
Okay, so we're working in a kind of unusual mathematical space where distance behaves a bit differently. What about the ring of integers and the maximal ideal?
The ring of integers, denoted by O, is a subset of F that acts a lot like regular integers. You can add and multiply within it, and it contains this special subset called the maximal ideal, which we denote by P. This maximal ideal has elements that are, in a sense, highly divisible by a special element we call the uniformizer.
And what exactly is this uniformizer?
It's denoted by O, and it's like the building block for the maximal ideal. Every element in P can be written as a multiple of O.
So it's like the fundamental unit of divisibility in this ring of integers. And what about the residue field?
The residue field, we denote it by FQ, and you get it by modding out the ring of integers O by the maximal ideal P. It's kind of like reducing everything down to its simplest form with respect to divisibility by O.
Got it. So we've got our field F with its unique distance, the ring of integers O with its maximal ideal P generated by the uniformizer A, and the residue field FQ. Now what about these important groups, G, Z, T, G0, K, K, P, I, and Psi, Pn?
Let's go through them one by one. G, our main focus, is GSp4F, the group of symplectic similitudes over the field F. They're basically matrices that preserve a certain geometric structure up to scaling.
So they keep the basic shape of things, even if they might stretch or shrink them.
Exactly. Then we have Z, the center of G. These are the elements that commute with everything else in G.
Okay, and T is the set of diagonal matrices in G. Those are the matrices with non-zero entries only on the main diagonal.
Precisely. And then there's G0. This is the set of all elements G and G whose similitude factor, which we denote by EG, is a unit in the ring of integers O. Remember, units are the elements with multiplicative inverses.
So G0 has elements with well-behaved scaling factors. What about K and Key, the compact subgroups?
K is simply GSp4O. It's made up of matrices in G where all the entries are from the ring of integers, O. Kp, on the other hand, is a bit more complicated. It's defined as the intersection of a specific matrix with entries from OP and P inverse with the group G0.
So Kp is a more specialized subgroup with stricter rules for its elements. What about I, the Iwahori subgroup?
The Iwahori subgroup I is defined as the intersection of another specific matrix this time with entries from O and O, the units of O with the group G.
Okay, so Kp and I, they're both defined by taking the intersection of specific matrices with larger groups. And finally, what about Cpn, the Siegel congruent subgroups?
These subgroups are really important for defining different levels of Siegel modular forms. They are defined as the intersection of yet another matrix 1 with entries from O and P to the N with the group G0.
Got it. It seems like all these subgroups, with their specific conditions on matrix entries, are essential for defining the representations in the spaces we're looking at.
Absolutely. They're the foundation for understanding how our representations are structured and for calculating the dimensions we're after.
Okay, we've covered a lot. We've defined the key groups and subgroups, and we've talked about how the paper uses double cossets to break down the dimension problem. Now, can we finally dig into these depth zero supercuspidal representations and see how they're built?
Absolutely. These representations, let's come from KP, they're constructed using something called compact induction.
Compact induction, what's that?
You can think of it as taking a representation from a smaller group, a subgroup of KP, and extending it to a representation of the larger group, G.
So it's like taking a blueprint and scaling it up to build something bigger.
That's a great analogy. To do this compact induction, we start with an irreducible representation, we'll call it, of the normalizer of Kp in G, denoted by NHK.
And the normalizer, that's like the stabilizer of Kp within G, right?
Exactly. Now, when you restrict to Kp, it has to be an inflation of a cuspidal representation of Kp plus M. This means that when you look at it just on Kp, comes from a specific type of representation of that quotient group.
Okay, so we restrict K2 and make sure it originates from a certain type of representation of this quotient group. Why is the quotient group so important?
Well, this quotient group, KTP plus S, it's isomorphic to GL22Q, which is made up of pairs of 2x2 matrices with entries from the finite field FQ, and the determinants of both matrices have to be equal.
So we're connecting our representation to a group of matrices over this finite field. What about the form of POO when it's restricted to Kp?
There are two possibilities. It's either a single irreducible representation, which we'll call us, or it's a direct sum of us and SU1, where U1 is a specific element in G. The second case happens when SES is not equivalent to SU1, which is like a twisted version of TUS that you get by conjugating it with U1.
So the form of PIP restricted to Kp depends on whether us is equivalent to its twisted version. To sum it up, our depth zero supercuspidal representation is built by taking a specific representation of the normalizer of Kp and inducing it up to the larger group G. The exact form of PID depends on the properties of...
You got it. Now that we have a grasp on how these representations are made, we can finally tackle those dimension calculations using the double cossets and their classification.
Yeah.
Ready to dive into the specifics.
Absolutely. Let's see how this mathematical puzzle unfolds. All right, I'm ready to see how we calculate these dimensions. Let's start with the double cossets. Can you remind me how they fit into all of this?
Remember, we're trying to find the dimensions of the spaces of Siegel invariant vectors within our depth 0 supercuspidal representation.
Right.
And to do that, we break down the group GSp4f into these double cossets of the form NGKP poem.
Right. Those are like the pieces of our puzzle.
Exactly. And the key idea is that the dimension of that space of Siegel invariant vectors in form, you get it by adding up the dimensions of certain subspaces, each linked to a specific double cosset.
So we add up the contributions for each double cosset.
Exactly. To make this calculation easier, we classify these double cossets into those 5 types: I, AC, Phi, AC, and 4. This helps us organize the calculations and see the patterns in the dimensions.
Okay, so let's talk about the types. Type I, you said it was the simplest one.
Yeah, type I double cossets. They're represented by these elements we call Tij, which are diagonal matrices with powers of a uniformizer along the diagonal.
Okay.
They're simple because they don't have the off-diagonal elements that you see in the other types.
So they're like the basic building blocks.
You could say that. Now, type 2, that one only exists when Q is even. Remember Q.
Yeah, the size of the residue field.
Right. Type 2 double cossets are represented by elements that look like this: Tijsxx0, where x is an element of the maximal ideal P, and its valuation, val x, has to be equal to I plus j.
Okay.
The reason it only exists for even Q comes from the specific way these double cossets are structured and how they interact with the Siegel congruent subgroup.
So the parity of Q matters already.
Yes, it does. Then there's type 3, which has 2 subtypes, II and I3.
2 subtypes.
Yeah. Both type 3 and Thipib, they involve more complex expressions than types 1 and 2. Type 3 double cossets are represented by elements of the form. Let's see, yi, jr, u, ti, j, js, 2i plus 1 plus r.
Okay.
And here u is a unit in the ring of integers.
These expressions are getting pretty complicated.
They are, but hang in there. Type 5 double cossets are also represented by yi, jr, u, but there's an extra condition. Jr has to equal 2.
Oh, so an extra constraint.
Yeah, this limits the possible values of ijr, which means you get a different count for the number of type 5 double cossets.
So both type and type psi involve these yijru elements, but with different rules.
That's right. Now for type 4, the last one, type psi double cossets are represented by elements of the form zu, ti, js, I plus j1 plus j1 plus j, where u is again a unit in O.
So all the double cosset types, except for type I, they all involve those S matrices with those off-diagonal entries.
Yes, and it's the specific powers of Ho in those off-diagonal entries, along with the conditions on I, J, and R that determine the classification of the double cosset.
This classification is really helpful for keeping track of all these different types.
It is, and the paper actually gives us a way to count how many of each type exist.
Oh, that's handy. How does that work?
We have lemmas 4.1 through 4.5, and they give us formulas for the number of each type of double cosset based on the values of n and q.
N and Q, right? The level of the Siegel congruence subgroup and the size of the residue field.
Right. For instance, lemma 4.1 says the number of type I double cossets is the floor of N124.
So it only depends on N in that case. What about the other types?
For types 2, 3, II, and 4, the formulas use both N and Q. And as we said earlier, these types only exist when Q is even.
There's that evenness popping up again. Prime number 2 is really calling the shots here.
Exactly. These formulas, with their dependence on N and Q, they highlight the complex relationships between these parameters and how the double cossets are structured.
Okay, so we've got our double cossets classified and counted. How do we actually use all this to calculate the dimensions of the spaces of Siegel invariant vectors?
That's where theorem 5.1 comes into play. This is the main theorem for the dimension formulas, and it splits things up into those 2 cases, when Q is odd and when Q is even.
Okay, let's start with Q being odd.
Right. When Q is odd, the theorem says that if the central character of S, which we denote by S, is not equal to 1, then the dimension of the space of Siegel invariant vectors in Mach is just 0.
So if the central character is not trivial, no Siegel invariant vectors.
That's right. But if the central character is equal to 1, then the dimension is given by a formula that uses the number of type I double cossets and a factor that depends on how, and its twisted version, you know one, are related.
Can you break down that formula?
Sure. The formula is dim Wunmus N124, a factor based on say it and infer. So the first part, N124, that's just the number of type I double cossets from lemma 4.1. The second part, it changes depending on whether a SA is equivalent to SA1. And if they are equivalent, it also depends on whether SA is equal to or strictly contained in the restriction of 1A2 to GL22.
Wait, hold on. 1 and 2, where did those come from?
Good catch. We need to go back a little. Remember that our depth zero supercuspidal representations, they're built from representations of the normalizer of Kp, which we call those representations are connected to representations of GL22Q, which is isomorphic to Kp plus.
Right, remember that connection. But how do 1 and 2 fit in?
Sometimes the restriction of tech Kp can be written using the tensor product of two irreducible cuspidal representations of GL2Q. We call those 1 and 2.
So 1 and 2 are these irreducible cuspidal representations of GL2Q that show up when we express in terms of representations of GL22Q.
Exactly. And that second factor in the dimension formula for odd Q, it depends on whether SA, which is a part of the restriction of Kp, is related to the restriction of 1, 2 to GL22Q.
So it all comes down to how Win fits into the bigger picture of these representations.
Okay, what about when Q is even? What happens to the dimension formula then?
When Q is even, things get a bit more complex because now all 5 types of double cosets have a say in the dimension. The theorem introduces a new function, fnq, to account for this.
If nq, what does it look like?
It's a piecewise defined function. It's 0 when n is less than or equal to 2, it's 1 when n is 3, and for n greater than or equal to 4, it's a more complicated expression with powers of 2, q, and the floor function.
Sounds complicated.
It is a bit, but it really shows how unique the prime number 2 is. That formula for fnq, when n is greater than or equal to 4, it reflects how 2 affects the structure of the double cosets when q is even.
So the dimension formula for even Q is basically this fnq, scaled by a factor that depends on whether it is equivalent to.
Exactly. That formula captures the contributions from all 5 types of double cosets and shows how n, q, and the properties of SOL all work together. Amazing. We've seen how the paper uses these double cosets and their classification to get these formulas for the dimensions, but there's still more to explore, right? What about that Aitken-Lehner involution and its signature?
You're right. The Aitken-Lehner involution adds a whole new layer of depth to this. Ready to dive into that?
Absolutely. Let's see what this mathematical mirror reveals.
All
right, let's talk about this Aitken-Lehner involution. It sounds like a pretty powerful transformation.
It is. It's denoted by un, and it's basically a specific element of GSp4f that has this flipping effect on our representations.
Okay.
It acts on the spaces of Siegel invariant vectors.
And why is it so important?
Well, the key is that it can actually change the dimensions of those spaces.
So it's like a mathematical mirror, reflecting our representations and maybe even resizing them.
That's a good way to think about it. And to measure this flitting effect, we use what's called the signature of the Aitken-Lehner involution.
The signature?
Yeah, we denote it by S. This signature, it basically tells us the difference between the dimensions of the plus and minus eigenspaces of un when it acts on the space of Siegel invariant vectors.
Okay, so the signature tells us how much the dimensions shift when we apply this involution. Does the paper give us a way to actually calculate this signature?
It does. Theorem 6.2 gives us formulas for psi n, and it breaks things down into cases for even and odd n and even and odd q.
Okay, let's start with n being even.
All right, when n is even and greater than or equal to 4, the theorem says that if q is odd, the signature is just 0.
So no change in dimensions for odd q and even n.
Right, but when q is even, the signature is given by this formula that involves q and a factor that depends on whether S is equivalent to its twisted version, psi 1.
Okay, and what is that formula exactly?
It's is n 1 plus qn for 2 times either 2 or 1, depending on whether psi is equivalent to a u.
Interesting. So for even q and even n, the signature is not 0, and it depends on both q and the relationship between the psi and what's the significance of that 1 plus q and 4, 2 part?
That part comes from the number of double cosets of types 2 and 4 that are fixed by the Aitken-Lehner involution. Remember, those types only exist when q is even, so they only contribute to the signature in that case.
Ah, right, because evenness matters.
It does. Now, when n is odd, the formulas for the signature get a bit more complicated, and there are different cases depending on whether q is even or odd.
Let's take even q first. What happens then?
When n is odd and q is even, the signature can be either positive or negative, and it depends on the specific choice of extension of u1 acting on SUD.
Okay.
The formula has 3 main scenarios. If SUD is not equivalent to SUS U1, the signature is 0. If SUS is equivalent to SUS U1 and n is greater than or equal to 5, the signature is on plus q and 4.
So even when SUS is not equivalent to SUS, the signature can be non-zero when n is odd and q is even. And that formula for n greater than or equal to 5, it involves both q and n.
Yeah, it's a linear dependence on n.
Okay, what about odd q?
When both n and q are odd, the formula for the signature brings in a new parameter, and it uses the central character of a representation, which we denote by co. The formula changes based on the relationship between sa and the representation or Harris.
Can you walk me through those different cases and how R and TO fit in?
Sure. If R is not equivalent to SUSO, the signature is 0. But if R is equivalent to SUSO, then we have a few possibilities. If R is equal to OR and OR is 0, the signature is N1. If R is equal to a specific quadratic character, which we call OA, the signature is 0. And lastly, if a force is strictly contained in OR, the signature is N1.
Wow, that's a lot of different cases.
It is, but Theorem 6.2 really lays out the complete picture of how the signature depends on N, Q, and all the different relationships between the representations.
So we have these general formulas for the signature, but does the paper give any specific examples to show how they work in practice?
It does. Corollary 6.3 looks at a special case where F is the field of two adic numbers, Q2, and its SUS is the unique irreducible cuspidal representation of GL2, F22.
So a very specific scenario.
Yeah, and in this case, there are two extensions of us to the normalizer of Kp, which we call plus and tuck. These give us two different representations, plus and tuck.
Two closely related representations. What does the corollary say about their signatures?
It gives us formulas for the signatures of p plus and pic, and again, it separates things based on whether n is even or odd. For n3, both representations have a signature of unhigh. But for n greater than or equal to 4, the formulas change depending on whether n is even or odd, and they behave differently for plus and tuck.
So this concrete example really helps to see how those abstract formulas actually work.
It does. Corollary 6.3 really drives home that connection between the Atkin-Lehner involution and the structure of these representations.
This has been a deep dive indeed. We've explored a lot, from defining the key terms to figuring out the dimension formulas and understanding this Atkin-Lehner involution.
It's been quite a journey.
It has. What are your final thoughts on this paper and what it all means?
I think this paper is a great example of how powerful p-adic representation theory is.
It really is.
It's a real display of mathematical ingenuity, revealing these hidden patterns and connections in these abstract spaces.
Definitely.
The formulas and theorems we've talked about, they give us real insights into how these depth zero supercuspidal representations are structured and how they relate to Siegel modular forms.
It's impressive how much detail and how many intricate connections this paper uncovers.
I agree, and this work, it opens up all sorts of new paths for research. For example, we could look into the generic versions of these representations.
Oh yeah, that would be interesting.
Right. Or we could explore how this connects to the Langlands program, or even look for applications in other fields like cryptography or physics.
So many possibilities.
Exactly. This deep dive has been a really exciting exploration of a fascinating mathematical landscape. It shows just how powerful human curiosity is and the endless possibilities in mathematics.
Well said. And on that note, we'll wrap up this episode of The Deep Dive. Keep exploring and keep pushing the boundaries of mathematical knowledge. Until next time. All right, ready to dive into some serious math.
Let's do it.
Today, we're looking at Jonathan Cohen's paper, Siegel vectors for non-generic depth, 0 supercuspidals of GSp4.
A bit of a mouthful, right?
Definitely. But the math inside is really interesting. We're in the world of p-adic representation theory.
Specifically for the group GSp4.
Now, someone might be thinking, hold on, haven't we already figured this stuff out?
Yeah, you might think that. But this paper tackles a problem that's still pretty wide open, figuring out the dimensions of spaces of fixed vectors. And these spaces are under the action of Siegel congruent subgroups, which even for specific representations like depth zero supercuspidals, we don't have all the answers.
Right, because even though these depth zero supercuspidals are like the basic building blocks in this theory, getting those dimensions is, well, it's tricky.
It really is. It's kind of like trying to measure a shadow. You know, the shape keeps changing depending on how you're looking at it.
I like that analogy.
But Cohen's approach is really clever. He uses these detailed character table computations and then this very meticulous way of classifying double causates.
And along the way, he finds this really cool divide between what happens with odd primes versus even primes.
Exactly.
Okay, let's start at the beginning. Page 1, the introduction. What's the big picture motivation here?
So Cohen connects his work to this classic problem, figuring out the dimensions of spaces of cusp forms. But these cusp forms are for certain congruent subgroups, all within SP4Q. It's a problem that goes way back in number theory.
But we already know those dimensions for some congruent subgroups, right?
Yeah, for some we do, but for others, like the Siegel congruent subgroup of level p to the n, well, those dimensions are still a mystery.
And this is specifically when n is 2 or greater.
Exactly, and that's where the representation theory comes in. Cohen really emphasizes that we need to look at the dimensions of spaces of fixed vectors, and these are for specific representations of GSp4 QP. But then they're under the action of certain local subgroups, which actually kind of mirror those global congruence subgroups.
So it's like we're trying to solve a global problem, but by looking for local solutions first.
Precisely. And Cohen makes it clear he's not trying to do everything at once. He focuses specifically on those depth zero supercuspidal representations.
Those building blocks we were talking about.
Right. And he points out that they can pop up in two ways. One from a maximal compact subgroup K, and the other from another compact subgroup that he calls KP.
But he doesn't really spend much time on those coming from K, right?
Not really. He mentions that the non-generic ones from K, well, they don't have any fixed vectors for any n, so they're not that useful for this problem.
Yeah.
So he shifts focus to the representations coming from KP.
That's where the action is.
Exactly.
Okay, on to page 2. This is where he lays out all the definitions.
Yeah. He brings in F, our non-archimedean local field. Then it's ring of integers, maximal ideal, and the residue field F sub Q.
And there's that assumption he makes, right? That if P equals 2, then F over Q sub 2 is unramified.
Right, can't forget that.
And then he throws in GL2 2Q. Seems a bit random at first.
It might seem that way, but it's actually super important. This group is key to understanding the structure of the representations he's looking at. It captures this double GL2 kind of nature that's hidden within GSp4.
Ah, okay, so it all ties together even if it's not immediately obvious. And then, of course, the star of the show, GSp4F.
Right. And he defines a bunch of important subgroups, like the maximal compact subgroups K and KP, the Iwahori subgroup. And don't forget that sequence of Siegel congruent subgroups. All of these subgroups have specific roles to play.
Like a cast of characters, each with their own little quirk.
Exactly.
And then he adds that isomorphism between KP over KP plus and GL2 2Q, even more that double GL2 theme.
Yeah. He also introduces some notation like 1 or 2. That's the restriction of the external tensor product from GL2Q squared to GL2 to Q. It sets the stage for really analyzing those specific representations he's after.
And then those matrix definitions, S1, S2, and UN. Important later on, I'm guessing?
Definitely. They're all related to the Weil group and the Akin-Lehner elements, which are crucial for understanding these representations. Think of them like tools we'll use to really get into the nitty-gritty details.
Tools of the trade. Got it. And then compact induction flashback to representation theory 101.
Oh, yeah, for sure. It's a way to build representations of a bigger group from those of a smaller one. And in this case, it's super important for building those depth zero supercuspidal representations we're after.
So he's laying out all the ingredients, like a recipe.
Right. He emphasizes that if a Kansai-Go supercuspidal representation of G, it can come about in one of two ways.
Okay, let's hear them.
The first is through compact induction from ZK. In this case, the representation, when restricted to K, is actually an inflation of an irreducible cuspidal representation of K over K+. The second way is through compact induction from NGP. Here, when we restrict the representation to KP, we get an inflation of a cuspidal representation of KP over K+.
Okay, so we've established where these depth zero supercuspidal representations come from. But what's the goal here? What's he trying to accomplish?
His goal is clear. Compute the dimension of the space of fixed vectors. But this is for under the action of Cp to the n, and this is for all those that come from Kp.
Right, because remember earlier we said that those arising from K aren't as interesting?
Exactly.
And he even mentions a companion article that's going to handle that K case, right?
Yes, he does. So the Kp case is where all the new stuff is.
Awesome. On to page 3.
Now we're getting to the heart of it. Cohen wants to calculate the dimension of the space of fixed vectors under the action of that Siegel congruent subgroup, Cp to the n.
Sounds pretty straightforward.
Well, to actually do this, he introduces this cool set called sup. It basically captures where the representation actually lives within the space of functions on G.
So instead of looking at the whole space, he's zeroing in on the parts that matter.
Exactly. And he breaks down the problem into two main tasks. First, figure out which elements are in sup.
Okay. Sounds reasonable. What's the second?
For each element G in sup, calculate the dimension of restricted to RG. Here is that representation of Kp over K plus that we get by restricting to Kp.
So it's a two-pronged attack. Figure out where the action is and then measure how much action there is.
Love that. And to tackle these tasks, he brings in this powerful tool, character table computations. That's what section 3.1 is all about. These tables are full of information about the representations of finite groups, and Cohen uses them strategically to get the dimensions he needs.
Character tables. Those always took me a while to wrap my head around.
Yeah, they can be pretty dense.
So how does he use them?
He starts with lemma 3.2, which focuses on specific subgroups R within GL2-2Q. These will actually turn out to be the RGs we're interested in. The lemma looks at different cases based on the structure of R, and then for each case, it calculates the dimension of SO restricted to R.
So he's building up a toolkit of dimension formulas.
Right. And before he even gets into the proof of the lemma, he adds this little remark that's easy to miss, but it's important. He points out that when Q is odd, the image of the center of KPP over KP plus actually has index 2.
Okay, that's pretty technical. What's the significance of that?
Well, it means that there's this element in the center of KP plus that doesn't come from the center of KB, and that helps us narrow our focus. Initially, we only know that the central characters of representations of Kp over K plus have to be trivial on the image of the center of Kp, at least if we want the associated compact induction to have Siegel vectors. But this lemma 3.2 actually shows us that the relevant representations, they have a trivial central character on the whole center of Kp over Kp.
Yeah.
So it's a subtle point, but it helps us narrow down the possibilities as we go forward.
So even the small details matter. On to the proof of lemma 3.2 then.
All right. Part A starts by assuming we have two irreducible cuspidal representations of GL2Q.
1 and 2.
Yep, those are the ones. And the product of their central characters is 1. This is crucial because it makes sure that the central character of SWAS, which is built from these two representations, will be trivial.
Okay, makes sense.
And the subgroup R in this case is pairs of matrices from GL2Q, but they have a specific structure. The second matrix is determined by the first. Now, Cohen really took advantage of the fact that 1 and O2 are cuspidal. This means their characters completely vanish on non-scalar matrices.
Which simplifies things, I imagine.
Definitely. The only contributions to the dimension come from elements that look like AI2, AI2. And when Q is odd, also from AI2, AI2.
Okay, so how do we actually calculate the dimension?
He uses the character table of GL2Q very meticulously. And what we find is really interesting. If Q is odd, the dimension is 1 plus toy 1.
Which depends on the central character of R evaluated at MIVL 1.
Exactly. But if Q is even, the dimension is just 1. And this difference between odd and even Q is something we'll see pop up again.
Foreshadowing, I like it. What about part B of lemma 3.2?
Part B is a little different. Here isn't just the restriction of 1O2 to GL2 to Q, it's a sub-representation of that restriction. The subgroup R, though, is the same as in part A.
And this only happens when Q is odd.
Yep, and when both 1 and 2 have reducible restrictions to SL2Q, meaning they break down into smaller representations when we look just at matrices with determinant 1.
Okay, I'm starting to see how these different cases create this intricate picture.
To really get into this case, Cohen brings in SPLUS and SPUC. These are equidimensional, irreducible representations of SL2Q. And both 1 and O, when restricted to SL2Q, decompose as the direct sum of SPUC and SUP.
So he's breaking things down further.
Yeah, exactly. And he uses the character table of SL2Q to show that the traces of SPLUS and SUP, they vanish on matrices of the form T inverse unless S is plus or minus 1. This really helps narrow down the possibilities for non-zero contributions to the dimension.
So he's using the properties of these representations to streamline the calculation. Very clever.
And then he shows that if X in FQ cross isn't a square, meaning it can't be written as the square of another element in FQ cross, then SUP applied to the matrix X, 1 actually swaps plus and SUP. This is a key observation for understanding how SPUP behaves on elements of R.
Okay, so we're seeing how these representations interact. What's next?
From there, he figures out that when restricted to SL2Q squared has to be one of two possibilities, either the direct sum of NES plus N square or the direct sum of plus E plus N smuzzy.
Right.
And this sets up the calculation for the dimension of cis restricted to R.
And how does that go?
He shows that if the determinant of the first matrix in an element of R isn't a square, then the trace of slus on that element is just 0. This happens because Ostwald is swapping those two parts in its restriction to SL2Q squared. So those contributions end up canceling each other out.
Ah, so he's using the symmetries to simplify things. I like it.
Right. But if that determinant is a square, say a squared, then that element can be broken down into a product. One part is AI2, and the other has determinant 1. This lets Cohen reduce the whole calculation to the trace of SON elements of SL2Q squared, which we've already figured out.
Breaking it down into manageable pieces.
Exactly. He then uses the character table to get the trace for the cases where the elements in SL2Q squared are either both plus or minus the identity matrix, or one is the negative of the other.
Lots of different cases to consider.
It is a lot. But by putting it all together, he gets this nice formula for the dimension of retrosh restricted to R, 1 plus STO2, 2.
And he even shows that per2, 1 is just 9-1 to the Q32 power. So there's this connection between the central character of 2 and the characteristic of the residue field.
Exactly. It's pretty neat. This formula gives us a concrete way to calculate the dimension in this case. It really shows how powerful those character tables are.
Agreed. Okay, what about part C?
Part C brings us to a different kind of subgroup R. This one consists of pairs of matrices that look like OUOOEA.
Where L belongs to FQ cross and U belongs to FQ.
You got it.
So each type of subgroup R brings its own challenge.
Absolutely. In this case, Cohen uses the character table for GL2Q and the fact that R is cuspidal to show that the trace of R on a matrix like O is just Toye, but that's only if U is non-zero. This really simplifies the calculation.
So he's always finding shortcuts.
Yep. He systematically figures out the dimension of SOS restricted to R by looking at all the possible pairs of matrices in R. It involves carefully thinking about when U is 0 and when it's not.
And the result?
The dimension of US restricted to R is Q1. It shows that even in these seemingly complicated situations, the math can be surprisingly simple.
Nice payoff for all that work. What about the last part of Lemma 3.2?
Part D takes us to even Q. And our subgroup R gets a little more intricate. It's made up of pairs of matrices that look like this. AU plus AD squared plus B AUA. Here, A is an FQ cross, and B and U are an FQ.
Okay, that does look more complicated. How does he handle this one?
He starts with an interesting observation. The number of elements that look like B squared plus B in FQ is exactly Q over 2. This becomes useful when we're counting different types of matrices in R.
So he's setting up a counting argument.
Exactly. He carefully calculates the dimension of restricted to R by considering all the possible pairs of matrices, using the character table of GL2Q and the fact that it's a cuspidal representation.
I bet that calculation gets a bit messy.
It does involve carefully thinking about the cases where B squared plus B is 0 and where it's non-zero. And he takes advantage of the fact that the trace of Y disappears on certain types of matrices because of its cuspidality.
So he's really pulling out all the stops.
Definitely. And after a bunch of steps, he arrives at a really nice result. The dimension of ZAR restricted to R is 1. This might seem simple, but it hides a lot of complex calculations and insights from group theory. It shows how deep Cohen's analysis is.
Wow, impressive. So we've made it through all 4 parts of Lemma 3.2. We built up this collection of dimension formulas for restricted to those specific subgroups R. Feels like a big accomplishment.
It is. These formulas, with their interplay between the characteristic of the residue field and the central characters, they give us a glimpse into these really intricate connections. These connections are between local and global properties in this part of math.
Very cool.
And they really set the stage for what comes next.
Okay, so we've tackled Lemma 3.2. What's next on our mathematical journey?
Now, Cohen brings in another key player, an involution that he calls cello in Lemma 3.3. This involution acts on our representation. And it does this by just swapping the order of the components in the tensor product. So cello is applied to V1 near, V2 gives you V2, V1.
Like flipping a coin, but instead of heads or tails, we're switching the order of our vectors.
Yeah, a good analogy. And this lemma looks at how a cell is in another operator, act on lim, but this is when cells is restricted to those subgroups R from lemma 3.2. And here W is a specific matrix, 0, 1, Naxo 1, 0 in GL2Q.
And why are we looking at these actions?
Understanding how JLs and SALU behave is super important when we analyze the signature of the Atkin-Lehner involution later on.
Got it. So it's another piece of the puzzle that we'll need down the road. So what do parts A and B of Lemma 3.3 tell us?
They deal with the case of even Q part A, shows that for each of those subgroups R we looked at in Lemma 3.2, the involutions as actually acts trivially on suds restricted to R, meaning it leaves every vector in that subspace unchanged.
So as is basically the identity operator in those cases.
Exactly. And part B goes a step further. It shows that for a particular subgroup R, the set of pairs of matrices, ABC, ABC inverse, with A, B, and C and FQ cross, the operator SUW also acts trivially on such restricted to R. But again, this is when Q is even.
So both E's and SUW are well-behaved for even Q. What happens when Q is odd?
Part C tackles that case, and it looks at that same subgroup R as in Part B. But here, the behavior of SUW is actually depends on a factor denoted as lec and the central character of R. So if the product lec is equal to 1, then both SUW is act trivially on restricted to R.
Okay, so that's similar to the even Q case.
Yeah. But here's where it gets interesting. If O is not 1, then O1 acts by -1 to the Q32 power, and O's acts with signature 0, meaning it has an equal number of +1 and -1 eigenvalues on that subspace.
Okay, so things get a little more complex when Q is odd and O is not 1. It seems like the parity of Q in this product will really play important roles in how these operators behave.
It really do. And before we get into the proof of lemma 3.3, Cohen introduces another lemma. Lemma 3.4. This one deals with a specific scenario. Imagine we have an irreducible representation of Kp over Kp plus, and it meets two conditions. Its central character is trivial, and O is not equal to its twist by the Atkin-Lehner element U1.
Hold on, remind me what twisting by U1 means.
Sure. Twisting by U1 means we're looking at the representation SO1,
Yeah.
and this is defined by ONG U1 in diverse. This is for any element G in the group.
Right. Okay, thanks. So what does lemma 3.4 say about this special representation?
It says that if we have an irreducible representation of NGK that contains the inflation of sus, and if R is a subgroup of Kp over Kp plus, and this subgroup is normalized by an element S in U1 Kp over K plus plus, then the trace of S restricted to R is 0.
Okay, that's a lot to unpack. What's the takeaway message?
The main point is that this lemma will be useful for understanding the signature of the Atkin-Lehner involution, especially in those cases where sus is not invariant under the action of U1. It's telling us that under these conditions, the contributions from different parts of the representation cancel out when we're calculating the trace.
Okay, so lemma 3.4 gives us another tool for analyzing the signature, but before we use it, we need to go through the proofs of these lemmas, right?
Exactly. Let's start with lemma 3.3. Parts A and B are assuming Q is even, and to make things a bit easier, we can replace rho with 2 to the negative 12 times. We're basically absorbing the factor U into the representation. This lets us just focus on the case where U is 1 and the central character of rho is also 1.
Another one of those strategic simplifications.
Exactly. We start with the subgroup R, the one made up of pairs of matrices, ABC, ABC inverse. A, B, and C are in FQ cross. To analyze this, Cohen brings in another subgroup, S, and this one consists of matrices that look like AB, where A and B are in FQ cross.
He introduces a lot of subgroups. How do they all fit together?
They each help us analyze the representations in a more manageable way. This particular subgroup S is helpful for understanding the action of R. Using the fact that rho is cuspidal, Cohen shows that the trace of rho on the matrix AB is just Q1 times the Kronecker delta function, which is 1 if A equals B and 0 otherwise. This actually implies that the dimension of rho restricted to S is 1, meaning there's a unique up-to-scaling non-zero vector in that subspace.
So we've isolated a special direction within the representation.
Right. Let's call this vector V. Now, Cohen argues that v(a) belongs to S restricted to R, and it's fixed by that swapping involution's S. This makes sense, right? Because swapping V and V in the tensor product doesn't change anything. And since rho W applied to V also has to lie in the space of rho restricted to S, it has to be a scalar multiple of V. Using the character table of GL2Q, we can actually show that rho W applied to V is vis V.
So we've figured out how rho W acts on this special vector V.
Right. Putting these pieces together, we see that rho WW applied to V is just rho WV, which equals V of V. And since lemma 3.2 tells us the dimension of restricted to R is 1, this means tro WW acts trivially on the whole subspace.
Nice. So we've shown that both is and joketown act trivially on tro restricted to R when Q is even. What about the other subgroups R?
Okay, for the next one, we look at the subgroup R with pairs of matrices of the form I, U, O, A, where A is an FQ cross and U is an FQ. For this one, Cohen brings in a non-trivial character from FQ to the non-zero complex numbers. Now, for each A in FQ cross, he defines a vector Va. This vector is in the representation space of Re, and it's unique up to scaling. It has the property that applied to the matrix 1u, 0, 1 acting on Va gives Phi A au u times Va for all u in FQ. And we know this vector Va exists and is unique because of how generic cuspidal representations of GL2Q are, which we can check using the character table.
So he's using this character to pick out these special vectors within the representation.
Exactly. With this setup, he shows that Cal applied to the pair 1u, 0, 1, 1, 1u, 1, acting on Va gives Ceph or Ova. Since Q is even, this simplifies to Va. This shows that Va is invariant under the action of this type of element in R.
So again, we're seeing this invariance under the action of certain elements.
Right. And remember, Lemma 3.2 told us that the dimension of sus restricted to R is Q1. Well, we can actually form a basis for this subspace using the vectors var of Va for all A in FQ cross. This means that S, that swapping involution, acts trivially on this whole subspace. It's just swapping the order of identical vectors in the tensor product.
So choosing the right basis is key here. It reveals that trivial action of S.
It really does. And for that last case, where R is the subgroup with those more complicated matrices involving A, U, and B, well, the conclusion follows right from the previous case. This is because restricted to this new R is actually a subspace of sus restricted to the R we just analyzed. So it inherits the trivial action of S.
Okay, so we've covered all three subgroups R for when Q is even. Now, what about odd Q?
That's where part C of Lemma 3.3 comes in. From Lemma 3.2, we know that the dimension of restricted to R, where R is that familiar subgroup, ABC inverse, is 2 in this case. Now, instead of directly calculating the signature of S, which would involve finding its eigenvalues, Cohen takes a different approach. He first calculates the signature of WWW on this two-dimensional space, and he shows that it's either 2 or 2 times 1 epino to the Q32 power, and this depends on whether Lo is trivial or not.
So he's finding a clever way to avoid that potentially messy eigenvalue calculation.
Exactly. And to do this, he uses the fact that the matrices involved are conjugate to each other, meaning they represent the same linear transformation, just in different bases. He also uses the characteristic polynomial of the matrix 1, A, 0, 1, which is x squared plus A. From the character table of GL2Q, we know that there's no contribution to the signature unless AA is a square.
Okay, so he's simplifying the calculation using properties of these matrices in the character table.
Right. And to handle the case where A is not a square, he brings in a character A from FQ squared cross to the non-zero complex numbers. This character corresponds to the representation, and its restriction to FQ cross is just the central character of A. So if A isn't a square, the trace of A applied to the matrix 1A, A1 squared can be written in terms of A evaluated at the square root of A.
So those characters are crucial for keeping track of everything.
They really are. This leads to a formula for the signature of AW, and it involves a sum over all A and FQ cross that are not squares. If AO equals 1, then this sum is just counting the number of non-squares, which gives a signature of 2. But if O is the non-trivial quadratic character, then the sum picks up a factor of -1 to the Q32 power for each term. And that gives us a signature of 2 times -1 to the Q32 power.
So the signature depends on both O and how many non-squares there are in the field.
Exactly. To actually figure out what S does, Cohen uses a specific way to represent. In this model, the space for the representation is made up of functions from FQ cross to the non-zero complex numbers. And the action of the matrix AB01 on a function f is given by ORB times f, evaluated at EPS-B.
So he's picking a specific way to visualize the action of R.
Right. This lets us view S as acting on functions from FQ cross times FQ cross to those non-zero complex numbers. The action of S just swaps the arguments of the function, and the action of elements from R involves scaling and shifting those arguments.
Okay, so we have a concrete way to see how these operators are acting.
Yeah. And using this representation, he builds 2 functions, F1 and F2. These form a basis for the subspace of S restricted to R. He then carefully analyzes how S acts on these functions. What he finds is that F1 is invariant under S, while F2 picks up a factor of war, where S is a fixed non-square in FQ cross.
So he figured out how S acts on this basis. What does that tell us about the signature?
Well, it means that if IDO is equal to 1, then S acts trivially on the entire subspace, because both basis functions are invariant. But if IDO is not 1, then S actually swaps the 2 basis functions, and that gives us a signature of 0.
So the signature of ISs hinges on the value of ILO. And that wraps up the proof of Lemma 3.3.
Yep. We've unpacked the actions of S in sets and SOBRI restricted to various subgroups R, and this lemma provides some great insights for when we explore the Aitken-Leonard involution later on. The interplay between the characteristic of the residue field, the central character of S, and that factor creates this really interesting landscape of possibilities.
It definitely feels like we're building momentum. We've got all these pieces in place. Now it's time to start putting them together.
You're right. Now we need to prove lemma 3.4, which focuses on the case where S is not equal to its twist by U1. Remember, this lemma gives us a condition for when the trace of S on restricted to R is 0.
Okay, so we're diving into another proof.
We are. The key idea here is that restricted to R can be broken down as the direct sum of sus restricted to R and so restricted to R. And since us normalizes R, S acts on this space. So we can compute its trace, but since us is not equal to SO1, the action of S essentially swaps these two components, and that leads to a cancellation of contributions. That's why the trace is 0.
So it's a really neat cancellation argument based on the structure of the representation. I'm starting to see the power of these techniques.
They're powerful for sure. And now that we have these lemmas, we're finally ready to tackle section 3.2, where we start the search for SUP.
Okay, we've made it to section 3.2. Time to do some detective work, huh?
That's right. We're hunting for those elements of SUP.
And Cohen starts by reminding us about a key decomposition.
Right.
For our group G, which is GSp4F.
Yeah, he breaks it down as the product INGTI, where I is that Ubuhori subgroup and NGT is the normalizer of the diagonal torus T.
Okay, that rings a bell. But how does it help us find those SUP elements?
Well, it gives us a really neat way to pick representatives. For the double cosets NGSIP to the N. These double cosets are like the building blocks for all of this. So having good representatives makes everything a lot easier.
It's like picking the right coordinate system. Makes the problem easier to see.
Exactly. By using the Iwahori factorization, and because KP contains representatives for NGT over T, Cohen shows that we can choose representatives that look like T, JS, XYZ. Here, TSS is a diagonal matrix with powers of the uniformizer, and SXYZ is a specific type of matrix with entries X, Y, and Z. And these guys belong to the maximal ideal P of our ring of integers.
Okay, so we have these representatives. Now what?
Now the fun begins. Cohen analyzes these representatives in detail. He uses relations within the group and properties of double cosets to put restrictions on the valuations of X, Y, and Z.
Right, because those valuations tell us about the size of an element in terms of powers of the uniformizer.
Exactly. So he's basically trying to narrow things down. For example, he shows that we can assume I is greater than or equal to 0 without losing any generality. And he demonstrates that we can make assumptions about the valuations of X, Y, and Z, relative to I and J. All these steps streamline the process of finding the SUP elements.
Like pruning a tree, getting rid of the branches that won't bear fruit.
Exactly. And lemma 3.5 comes in with even more refinements to these restrictions.
Oh, yeah. What kind of?
Well, part A of this lemma tells us that if X isn't 0, we can assume that 0 is less than or equal to I, plus the valuation of Y divided by X.
Okay, so that's another constraint on the relative sizes of X and Y.
Right. And part B adds another layer. It focuses on the case where X, Y, and Z are all non-zero, and the valuation of Z has a specific relationship to the valuations of X and Y. In this scenario, we can assume that I plus the valuation of Y divided by X is less than or equal to E1. And here, E is the valuation of 2 in our field F.
So now the properties of the field F, especially how the prime 2 behaves, are starting to play a role.
Exactly. To refine our search even further, Cohen introduces two subgroups, U1 and U2, within GL2.
More subgroups. We're bringing in the whole team.
They're important, though.
Yeah.
They have a specific structure, and they're key for eliminating potential candidates for SUP.
How so?
The key is that if RG, that intersection of a conjugate of SUP to the N with K pair, contains either U1 or U2, then the restriction of SUP to RG is just 0. And this is because of the cuspidality of SUP. It forces the character to vanish on certain types of matrices.
So if RG contains U1 or U2, we can cross that double coset off our list.
Yep, exactly. And lemma 3.6 puts this elimination strategy into action. It gives us more restrictions on I, J, X, Y, and Z, all based on the fact that RG shouldn't contain U1 or U2.
So we're using those subgroups to eliminate possibilities and really shrink that search space.
Right. Part A of lemma 3.6 looks at the possible values of J. It shows that J has to be between 1 and N2I for a double coset to even have a chance of being in SUP. Parts B and C then give bounds on the valuations of X, Y, and Z. These bounds make sure that certain entries in the matrix, representatives for the double cosets, have large enough valuations. And this keeps RG from containing U1 or U2.
So we're really squeezing out those unwanted double cosets with all these constraints on the valuations.
Yeah. Lemma 3.7 introduces yet another player, the Siegel-Levi subgroup, denoted M. The subgroup has matrices in G, but with a specific block structure. And it helps us relate sup to a smaller, easier-to-handle subset of G.
We're zooming in on the good stuff.
Exactly. The lemma says that if a double coset represented by G is in SEP, we can write it as NGSIP to the N intersected with M. This is super helpful because it means we can just focus on the intersection of sup to the N with the Siegel-Levi subgroup when we're analyzing RG.
Okay, so we've simplified things by focusing on this smaller intersection.
Right. And because of lemma 3.6, we can now focus on 4 specific forms for the representative G. Each form has its own set of constraints on the variables.
Lay them on me.
All right, the first form is just G equals tie J. The second is G equals tie JSX 0, 0, 0, where X is non-zero and its valuation has a lower bound. The third form is G equals tie JS 0, YZ, where Y is non-zero, its valuation has an upper bound, and the valuation of Z is linked to the valuation of Y. And lastly, we have G equal tie JS XYZ, where all 3 variables are non-zero, the valuation of Z is tied to the valuation of Y, and there's an extra constraint on the valuations of X and Y. And that last constraint depends on whether Q is even or odd.
So we've got 4 specific forms to work with.
Yep. And lemma 3.8 swoops in and gives us the final piece of the puzzle. It gives the necessary and sufficient conditions for each of these 4 forms to actually be in supercuspidal.
That sounds like a huge result.
It really is. It's the culmination of all that careful analysis. It's like a roadmap showing us exactly which double cosets are important.
We finally found the treasure map. Now we just need to figure out how much treasure is buried at each spot.
Exactly. And that's where section 4 comes in. It's all about counting those double cosets. We need to know how many of each type contribute to the dimension. And there are lots of detailed calculations and clever counting arguments to help us.
Let's get counting then.
All right. Cohen starts off with an important observation. Since the double coset G tells us the structure of RG to conjugacy within Kp over Kp+, and we've already categorized RG for each type of double coset, there can't be any equalities between double cosets of different types. This really simplifies our counting.
We don't want to count the same treasure chest twice.
Exactly. Plus, the conditions in lemma 3.8, they make sure that if a double coset like TJS_XYZ is in sup, then the values of I and J are unique. And the valuations of X and Y, when those are non-zero, are also unique. This means that to count the double cosets, we just have to count the possible combinations of I, J, and the valuations of X and Y. Of course, we have to keep in mind all the restrictions we found.
So break down the problem into smaller chunks. Makes sense.
Right. So lemma 4.1 tackles the simplest case, counting those type I double cosets, represented by G equals TJ. Using the constraints on I and J from lemma 3.6 and a clever summation trick, Cohen shows that the number of these double cosets is the floor of n1 squared divided by 4.
So the number of type I double cosets grows kind of like n squared.
Yep, and lemma 4.2 looks at those type 2 double cosets. Those are represented by G, partio S, 0, 0 with even Q, and the valuation of X being I plus J. What Cohen finds is that if n is less than or equal to 3, there aren't any of these double cosets. But if n is at least 4, then the number of type 2 double cosets is the floor of n2 squared divided by 4.
That n squared growth pattern again.
It is. Now, for types 3 and 4, the counting gets a bit trickier, because now we have the variable u to deal with, which represents an element of the residue field.
Right, that makes things more complicated.
It does. For type 3 double cosets, which are represented by G equals T, JS0YZ with even Q, Cohen shows we can actually assume Z is a power of the uniformizer. We don't lose anything by making this assumption, and it lets us focus on counting double cosets that look like T, JS0Us to the R, O to the 2I plus 1 plus R. Here U is in all cross modulo, 1 plus P to the JR. Using some matrix calculations in group theory, he shows that the values of I, JR, and U, where we're considering U modulo squares and O cross times 1 plus P to the JR, make up a complete set of invariants for these double cosets, meaning each unique double coset is determined by these 4 values. This means we can count them by simply figuring out how many combinations of these values there are. It's like he's found a way to label each treasure chest so we don't overcount.
Exactly.
Lemma 4.3 focuses on type II double cosets, where JR is 1. What he finds is that if n is less than or equal to 3, there aren't any of these double cosets. But if n is at least 4, The number of type II double cossets is the floor of n3 squared divided by 4.
There's that n squared growth again. It's everywhere.
It is. Now, lemma 4.4 tackles the type IIB double cossets. Those are the ones where JR is 2. This time the count involves Q, the size of the residue field. If n is less than or equal to 3, we're out of luck. There are no double cossets of this type. But if n is at least 4, the number of type IIB double cossets is Q times the floor of n5 squared divided by 4.
So the size of the residue field matters now, too.
Right. And finally, we get to those type IV double cossets. These are represented by GIT, JS, XYZ, with even Q and J minus the valuation of Y being 1. Cohen shows that we consume both X and Z are powers of the uniformizer. This lets us just focus on double cossets of the form tie JS, O's to the K, O's to the R, O's to the 2I plus 1 plus R, and again, U is in O cross modulo 1 plus P to the JR. He looks closely at the conditions from lemma 3.8 for these double cossets. He finds that K has to be I plus J1 and R has to be J1. And with a bit of matrix work, he shows that if two of these double cossets are equal, the difference between their U values has to be in the maximal ideal P. This means that for specific values of I and J, there are exactly Q1 distinct double cossets of this form. Lemma 4.5 then uses this to count the total number of type IV double cossets. When n is less than or equal to 3, there aren't any. But for n at least 4, the number is Q1 times the floor of n4 squared divided by 4.
Okay, that was a lot of counting. But it feels like we've achieved something big. We've counted all the double cossets that matter for the dimension.
We have. Each formula gives us a concrete way to figure out the size of sup. And we even see how n and q play a role in each one.
I'm exhausted but happy.
Yeah.
It's amazing how Cohen systematically tackled this counting problem. He used group theory, matrix calculations, and those valuations all working together.
He really is a master at work. Now that we understand sup, we can finally get those dimension formulas. This is what we've been working towards. And it's all in section 5.
The grand finale. Let's hear it.
Okay, so Cohen starts by looking at the case where restricted to KAP is the direct sum of so-and-so. In this case, the dimension of restricted to RG is just the sum of the dimensions of restricted to RG and so on restricted to RG. We can use those formulas from lemma 3.2 right away.
So that case is pretty straightforward.
Yeah. But when restricted to K is just sus, meaning sus is invariant under U1, things get a bit more complicated. We have two possibilities. If sus can be written as the restriction of ROU, where pura is an irreducible cuspidal representation of GL2Q and O is a specific character, then the dimension of first restricted to RG is simply the dimension of restricted to RG. But if Q is odd and sus isn't of this form, then it has to be a subrepresentation of the restriction of And in this case, the dimension of is restricted to RG is either 1 or 0. It depends on whether Q is congruent to 3 modulo 4 or congruent to 1 modulo 4.
Okay, so the dimension calculation depends on the specific structure of sus and the residue field characteristic.
Exactly. All of this, plus the fact that when Q is odd, the only double cossets that matter are those of tight I, leads to a really nice dimension formula. It's theorem 5.1. This theorem says that if Q is odd, the dimension of restricted to sus to the n is 0 unless the central character of sus is trivial. And if the central character is trivial, then the dimension depends on how sus and su are related.
So the theorem captures how the residue field characteristic, the central character, and the relationship between soy and its twist all play a role.
You got it. And when Q is even, the formula gets even more interesting. It involves a function, fnq, which captures the total contribution from all 4 types of double cossets. Theorem 5.1 tells us that if Q is even, then the dimension is fnq times 2 if is not equal to its twist, and just fnq if they are equal. The way fnq is defined actually changes depending on the value of n.
So for even Q, we need to consider all those different types of double cossets we analyzed.
Yep. And to give a specific example, Cohen presents corollary 5.2. This specializes the dimension formula to the case where f is Q2, the 2 adic numbers, and in this case, the formula becomes much simpler.
So we've gone from abstract representations to concrete formulas for their dimensions. That's amazing.
It is, and now that we have these dimensions, we can move on to the Atkin-Lehner involution. This involution acts on the space of fixed vectors. It adds another layer of structure and symmetry to our analysis.
Okay, we're bringing in another tool. What can you tell me about it?
All right, so Cohen dives into the Atkin-Lehner involution in section 6. To keep things organized, he introduces some abbreviations. He uses XK, E, J, R, U, and ZU are for types 2, 3, and 4 double cussets.
Those will definitely be helpful.
They will. So lemma 6.1 gets us started. It shows how the Aitken-Linear involution acts on functions in the space of fixed vectors, and it looks at each type of double cusset separately. It reveals how the involution interacts with those specific representatives.
So we'll see how it moves those double cussets around.
Exactly. Part A of lemma 6.1 looks at the type I double cussets, those represented by 2 cussets. It says that if f is a function in the space of fixed vectors, then applying the Aitken-Linear involution un to f and then evaluating at TOI is the same as applying u1 to f and evaluating at TOIN to ij. This shows how the involution shifts the argument of the function. But it also brings in this factor of 2-1. Remember, u1 is that special element in GP.
So it's not just rearranging things, it's also bringing in this extra factor.
Right. The lemma then shows that a double cosset G is fixed by the involution if and only if n is odd and equal to 2i plus 2j plus 1. And if n is odd, there are exactly n12 type I double cossets that are fixed by un.
Okay, so we found the type I double cossets that don't move.
Yep. Part B of lemma 6.1 looks at type 2 double cossets, those represented by tie jxk, where q is even and k is I plus j. It shows a similar identity to part A, relating applying un to a function at tjxk to evaluating the function at a potentially different representative. Then the lemma shows that g equals gun if and only if n is even and equal to 2k, and if n is even and at least 4, there are n22 type 2 double cossets that are fixed by un.
So the fixed double cossets depend on whether n is even or odd and what the representative looks like. That seems to be the pattern.
It is. Part C deals with type 3 double cosets, which are represented by U, J, R, U, where Q is even, and 1A, J, R, A, 2. This one gives a slightly more complex identity. It involves both HU1 and A1, 1U. Then the lemma says that G equals gun if and only if n is odd and equal to 2i plus 2r plus 1. It also gives a precise count of the fixed double cosets for each subtype of type 3.
So really breaking down how the involution acts on each type of double coset.
We are. And finally, Part D looks at type IV double cosets. These are represented by Z, gray U, where Q is even. It gives an identity showing how applying un to a function at Z or U relates to evaluating the function at a potentially different representative. Then it says that G equals gun if and only if n is even and equal to 2i plus 2j2. And if n is even and at least 4, there are Q1 and 4-2 type IV double cosets fixed by un.
Phew. Okay, so lemma 6.1 gives us a complete picture of how that Aitken-Linear involution works on our double cosets. We know how it rearranges them, and we know exactly which ones stay put.
Right. And that brings us to the signature of the involution. Theorem 6.2 gives us a formula for the signature of this Aitken-Linear involution on the space of fixed vectors.
This feels like the culmination of all our work.
It is. The theorem separates things based on whether n is even or odd, because the involution behaves differently in those two situations. So for even n, greater than or equal to 4, the signature depends on q. If q is odd, the signature is 0, but if q is even, the signature involves the factor, 1 plus qn 4, 2, and we multiply that by 2 if is not equal to its twist by u1, and by 1 if they are equal.
So even or odd q matters, and so does the relationship between c's and its twist.
Yep. For odd n greater than or equal to 3, it gets even more interesting. If q is even, the signature is either plus or minus a certain value. That value depends on how us and its twist are related and the value of n, and whether we pick plus or minus actually depends on how we extend the representation from kp to ng. It reflects a certain ambiguity in the construction.
Wow, so even subtle differences in how the representation is built can change the signature.
They can. And if q is odd, the signature formula involves the factor, n12, and it depends on the specific form of sun. There are different cases based on whether sus is equal to its twist and whether it can be written in a specific form involving an irreducible cuspidal representation of GL2Q.
It's incredible that Cohen managed to capture all these details in a single formula.
I know, right? It's pretty remarkable. And to give a concrete example, he presents corollary 6.3. This one specializes the signature formula to the case where F is Q2 and sun is the unique irreducible cuspidal representation of GL2 of 2 squared. This corollary gives a simplified formula for the signature, and it just depends on whether n is even or odd and how we extend.
So we see how those general results work in specific cases. What a journey. It's been amazing to work through all those lemmas, theorems, and corollaries.
It really has. We started with the motivation for Cohen's work. Then we looked at all that intricate setup, analyzed those double cosets in detail, derived the dimension formulas, and explored the Aitken-Linear involution. It's been exciting to see all those concepts, arguments, and results come together.
I feel like I have a much better grasp on these representations and the tools we can use to analyze them.
That's great to hear. And I hope this deep dive encourages everyone to keep exploring. There's a whole world of p-adic representation theory out there just waiting to be discovered.
Absolutely. There's always more to learn. Thanks for taking us through this amazing paper. I can't wait for our next deep dive. Okay, strap yourselves in because today we're going deep, like seriously deep into number theory.
Oh, yeah.
We're going to be tackling this paper, Siegel Vectors for Nongeneric Depth, 0 Supercuspidals of GSp4 by Jonathan Cohen.
Sounds intense.
It is. So this paper kind of grapples with this problem that's fascinated mathematicians for ages.
Right.
And that's figuring out the dimensions of certain spaces of Siegel modular forms.
Yeah.
You might be wondering, like, what even are Siegel vectors? And why do we even care?
Good question.
Well, think of them kind of like keys to unlock the secrets of these, like, mysterious dimensions.
Oh, I that.
We've got a stack of resources for this one. So we've got the paper itself, of course.
Of course.
And some background on Siegel modular forms.
Always helpful.
And we've even got some character tables.
Nice.
So we're well equipped to unravel this mathematical puzzle.
I think so.
So to get us started, can you kind of give us a lay of the land? What are Siegel modular forms? And why do mathematicians care so much about their dimensions?
Okay, so what's fascinating about Siegel modular forms is they act like bridges between different areas of math.
Okay.
So they connect number theory, complex analysis, even physics.
Wow.
They've got these special symmetries that make them super valuable for studying things like quadratic forms and lattices.
Right.
The dimensions of the spaces they live in, those encode deep arithmetic information. But here's the catch.
Right.
For certain types of Siegel modular forms, like those associated with Siegel, congruent subgroups of level p to the n, where n is greater than or equal to 2,
Right.
we don't actually know those dimensions.
Oh, wow.
It's a problem that has puzzled mathematicians for years.
So it's like we have this vast uncharted territory
Exactly.
within the world of Siegel modular forms.
Exactly. And that's
Yeah.
what makes this paper so exciting.
Yeah.
Cohen tackles this problem by focusing on a very specific type of representation. It's called a depth 0, irreducible, non-generic supercuspidal representation of GSp4f.
Woof, those are some intimidating words.
I know, right?
Can you break that down for us? What is a depth 0 supercuspidal representation?
Okay, so think of it as a special kind of mathematical object
Okay.
that describes symmetries and transformations.
Okay.
In this context, depth 0 refers to a particular property of this representation. And supercuspidal tells us it's a very, very special and fundamental kind of representation.
Okay.
These representations are particularly relevant to understanding the spaces of Siegel modular forms we're interested in.
Okay, so Cohen is using these representations as tools
Yes.
to probe the mysteries of those dimensions.
Yes.
And why the focus on non-generic representation?
Okay, good question.
What makes them different?
So non-generic simply means these representations have certain special properties
Okay.
that distinguish them from the more common generic ones.
Right.
Mathematicians have already made significant progress in understanding generic representations. So focusing on the non-generic case allows Cohen to explore a new frontier,
Cool.
potentially uncover hidden patterns and relationships.
So it's like venturing into uncharted mathematical waters.
Precisely. And as we delve into the paper, we'll see how Cohen cleverly uses these non-generic representations to shed light on this dimension problem.
Yeah.
He utilizes a very powerful technique called the Aitken-Lehner involution,
Okay.
which is a kind of transformation that helps reveal symmetries within these spaces.
Okay, I'm definitely intrigued. So let's dive into the paper itself.
All right, let's do it.
What is Cohen's main strategy for tackling this problem?
Cohen's approach is a really masterful blend of representation theory and these intricate calculations.
Okay.
He cleverly reduces the dimension problem to a seemingly unrelated problem,
Okay.
figuring out the number of certain double coset. Think of double cosets as a way of grouping elements together based on their relationship to two specific subgroups.
Okay.
Cohen then utilizes character tables,
Okay.
which are essentially cheat sheets for understanding representations,
Right.
to compute those dimensions.
Character tables, I remember those from linear algebra.
Yeah.
But can you give us like a quick refresher?
Of course. So Character tables summarize information about the characters of a group,
Okay.
which are special functions associated with representations.
Right.
Each entry in the table corresponds to a specific character value for a given group element. By cleverly manipulating these tables,
Yeah.
Cohen can deduce crucial information about the dimensions he's seeking.
So it's like decoding a secret message
Exactly.
hidden within those character tables.
Exactly. And that's just one of the ingenious techniques Cohen employs.
Wow.
He also meticulously parameterizes something called sup. You can think of this as a map that keeps track of all the relevant double causates for the representation in question.
Got it.
By studying sup, Cohen can then enumerate those double causate, bringing us closer to those elusive dimension formulas.
This is starting to sound like a real mathematical treasure hunt.
It definitely is.
Yeah.
And along the way, we'll encounter a common theme in number theory.
Okay.
The fundamental difference between cases where p equals 2 and p is greater than 2.
Right.
This dichotomy pops up surprisingly often.
Yeah.
And Cohen's paper explores how it affects the calculations and formulas involved.
Okay, I'm ready to embark on this mathematical adventure.
Awesome. Let's go.
Let's start by setting the stage.
Okay.
What are some of the key definitions and notations we'll need to understand?
Sure. So Cohen starts by introducing the field f,
Okay.
which is a finite extension of the p-adic numbers, denoted qp.
Right.
Since we're working with a finite extension of qp, we have the ring of integers, denoted by a lowercase o, and the maximal ideal p.
Right.
We also have O, which is a uniformizer,
Uh-huh.
and FQ, the residue field.
Okay.
These are all standard objects in p-adic number theory.
Gotcha.
He also imposes an interesting condition, that if p equals 2, then f over q2 must be unramified.
Okay, interesting.
This condition simplifies some of the calculations later.
Okay, so those are the basic building blocks of our mathematical playground.
Right.
What are the main players in this story, the groups we'll be working with?
Okay, so Cohen introduces several important groups: GL22Q, GSp4f, Z, T, G0, K, KPI, and CPI to the N.
Wow, that's a whole family of groups. Can you give us like a quick rundown of what they represent?
Of course. So GL22Q consists of pairs of 2x2 matrices with entries from the finite field FQ, where both matrices have the same determinant.
Okay.
It's a specific subgroup of the direct product of two copies of GL2Q,
Okay.
which is the group of all invertible 2x2 matrices over FQ. The symplectic group, denoted GSp4f, is defined in terms of a specific 4x4 matrix J. It consists of matrices that preserve a particular kind of geometric structure.
Right.
Z is the center of GSp4f, containing elements that commute with everything else.
Right.
T is the subgroup of diagonal matrices.
Yeah.
G0 is a subgroup defined by a condition on the multiplier, which is a function associated with each element of GSp4f.
Got it.
K is the standard maximal compact subgroup, GSp4o.
Okay.
And KP is another maximal compact subgroup defined in terms of a specific matrix structure.
Yeah.
A is the standard Iwahori subgroup,
Uh-huh.
and AP to the N are the Siegel congruent subgroups we've already mentioned.
Okay. That's a lot to keep track of, but I'm starting to get a sense of the cast of characters involved.
Good. And just like in any good story, each of these groups plays a specific role
Yeah.
and interacts with the others in interesting ways.
So we have our stage set, our characters introduced. What's the first act of this mathematical drama?
So Cohen begins by defining KOP plus US, the pronipotent radical of KP.
Okay.
This is like the wild child of KP,
Yeah.
a subgroup that captures its most unruly elements.
Got it.
Then he establishes a crucial connection between two seemingly unrelated groups.
Okay.
He shows that KP plus, which is formed by collapsing, KP plus K, is isomorphic to GL22Q, the group we encountered earlier.
Okay, so they have the same underlying structure.
Exactly. This means they have the same underlying structure.
Right.
This isomorphism will allow Cohen to translate information from one setting to another, which is a powerful technique.
Oh, cool. Okay, so he's building bridges between different mathematical worlds.
Yeah.
What else does he set up in this initial stage?
He defines three specific matrices.
Yeah.
S1, S2, and UN.
Okay.
S1 and S2 are 2x2 matrices that generate the whale group, which is a group that captures the symmetries of the root system associated with GSp4f.
Right.
Think of the root system as a way of understanding the structure of GSp4f, and UN is the Atkin-Lehner element.
Right.
A special matrix that will play a crucial role in our analysis later.
Okay, so we have these special matrices waiting in the wings. ready to make their entrance.
Precisely. And finally, Cohen introduces a powerful technique called compact induction, denoted secant,
Okay.
which is used for constructing representations of larger groups from representations of smaller subgroups.
Right.
This method will be essential for understanding how representations behave as we move between different groups in our analysis.
Okay, so compact induction is like a tool for building bigger structures from smaller ones.
Exactly.
With these definitions and tools in hand, Cohen then focuses on the case where the depth zero supercuspidal representation is obtained from Kp.
Yes.
This specific choice will allow him to exploit the properties of Kp and make progress on the dimension problem.
Exactly.
I'm already sensing the elegance and complexity of Cohen's approach.
It's a really cool paper.
Let's move on to the next stage of his strategy. In section 3, titled Siegel Vectors for equal C from NGKP Apri, Cohen dives into the heart of the problem.
Yes, he does.
He focuses on a specific type of depth zero supercuspidal representation, one that is obtained by compactly inducing a representation from NGKP2.
Yeah.
Remember, is an irreducible representation of NGP, and its restriction to Kp is an inflation of a cuspidal representation of Kp plus Ekachik.
Right.
Right, we touched on that earlier. But before we go any further, can you remind us what Siegel vectors are and why they're so important for this problem?
Okay, so a Siegel vector for representation is a vector that remains unchanged under the action of the Siegel congruence subgroup NG to the n. Think of it as a fixed point for this subgroup's action.
Okay.
Calculating the dimensions of the spaces spanned by these Siegel vectors is a key step in understanding the larger structure of these representations and their connection to Siegel modular forms.
Okay, so those Siegel vectors hold the key to unlocking the dimensional mysteries.
Yeah.
What's Cohen's game plan for finding them?
He introduces a clever strategy involving double cosets and character table computations.
Okay, love it.
He starts by defining 3 crucial objects.
Right.
G, RG, and sup for a fixed NOA0 and an element G in G.
Yeah.
G represents the double coset NG TSP to the n.
Right.
This is simply a set of elements in G related to G through multiplication by elements from NG SCP on the left and psi p to the n on the right.
So it's like grouping elements of G based on their relationship to those 2 specific subgroups.
Precisely.
Next comes RG, another subgroup related to G.
Right.
It's defined as the intersection of GSAP to the NG inverse with KEP modulo KP plus E. Okay, I'm following so far. What about sup? What role does it play in this story?
Sup acts like a filter, selecting the important double cosets relevant to our representation.
Okay.
It consists of all double cosets G for which the representation, when restricted to the subgroup RG, is non-zero.
So sup helps us zero in on the double cosets that really matter.
Exactly. And Cohen shows that the dimension of the space of Siegel vectors for is equal to the sum of the dimensions of SFO, restricted to R, summed over all those special double cosets in sup.
Okay, I see the brilliance of this approach. He's breaking down a seemingly intractable problem into smaller, manageable pieces.
Yeah.
Now, to conquer those pieces, he needs to determine sup and then calculate those dimensions.
Right, exactly. And that's where those character tables we mentioned earlier come into play.
Okay, I'm eager to see how he wields those character tables to crack this code. But looks like we've reached the end of our time for this segment.
Okay.
So let's pick up this mathematical adventure in part 2 of our deep dive.
Sounds good.
All right, see you then.
See you later. So those character tables, those are like hidden treasure maps,
Right.
guiding us towards the solution.
Yeah.
Cohen, he uses them to compute the dimensions of restricted to those crucial ARGI subgroups.
All right.
And remember, those dimensions, those are like the building blocks for his dimension formula.
All right, those character tables are like, I don't know, like a secret code
Yeah.
to break to get to the answer.
Exactly. To decipher those maps, Cohen uses information about the characters of certain finite groups
Okay.
related to those RG subgroups.
Right.
So it's a clever trick, right?
Yeah.
By studying these smaller finite groups,
Yeah.
we can gain valuable insights into the characters of the original p-adic groups,
Right.
which are much more complex.
It's amazing how seemingly disparate areas of math can connect in such unexpected ways.
I know, right? It's really cool.
So where does Cohen delve into these character table calculations?
He weaves those calculations into the proofs of various lemmas and theorems throughout the paper.
Okay.
A particularly illuminating example is in the proof of lemma 3.2,
Okay.
where he tackles the problem of finding the dimensions restricted to various R subgroups.
Ah, Lemma 3.2. That's the one with all those dimension formulas that depend on the specific form of the subgroup R.
Exactly. Cohen carefully analyzes the structure of each R subgroup. Okay. And then uses character tables of certain finite groups to derive those formulas.
Right.
For instance, in Part A of Lemma 3.2, he considers a specific subgroup R of GL2 2Q. And shows that only elements of a particular form within R actually contribute to the dimension calculation.
Oh, wow.
He then cleverly utilizes the character table of GL2Q to calculate the character values for these special elements, leading him to the dimension formula.
So it's like a delicate dance between group theory and character theory.
It is.
Each step revealing a bit more of the solution.
Exactly.
And Cohen repeats this elegant dance throughout the paper, tackling each case with precision and insight. He also doesn't stop there.
No.
He goes on to explore some fascinating properties of the Aitken-Lehner involution.
Right, that Aitken-Lehner involution, that's a good one.
Ah, yes, the Aitken-Lehner involution. We've talked about its signature.
Yes.
But what other secrets does it hold?
Well, Cohen delves into how the Aitken-Lehner involution interacts with those double causates in SUP.
Okay.
And he discovers that in certain cases, the involution actually fixes specific double causates, meaning it maps them onto themselves.
So it's like the involution is shuffling those double causates around.
Yeah, it's a good way to think about it.
Sometimes leaving them in place and sometimes moving them to new positions.
Yeah, exactly.
And this shuffling act provides valuable information about the structure of those spaces of Siegel vectors.
Exactly.
Okay, so Cohen is really squeezing every drop of insight he can out of this Aitken-Lehner involution.
He is. He's very thorough.
All this work ultimately feeds into those dimension and signature formulas that are at the heart of his paper.
Yes.
Now that we've explored those character table calculations and delved deeper into the Aitken-Lehner involution, let's return to Cohen's main strategy for tackling the dimension problem.
Okay.
Remember, he cleverly linked the dimension of the space of Siegel vectors to a seemingly unrelated problem. Counting double causates.
Right. Very clever.
Once he sets up the connection between the dimension of the space of Siegel vectors and the dimensions of spawns restricted to those RG subgroups, the task becomes figuring out precisely which double causates belong to SUP. And then counting them.
Exactly.
Okay, so it's like a two-pronged attack.
Yeah.
First, identify the relevant double causates, and then figure out how many there are.
Exactly.
And Cohen tackles this challenge in section 3.2.
Yes.
Where he begins to determine SUP.
Right.
He utilizes a well-known decomposition of GSp4f. GSp4f is equal to INGTI, where I is the Giwa-Hori subgroup, and NGT is the normalizer of the diagonal subgroup T.
Yeah, that's a good decomposition to use.
So he's breaking down that big, complicated group GSp4f into smaller, more manageable pieces.
Yeah, exactly.
This decomposition, along with some clever manipulations, allows him to write down a convenient set of representatives for the double causates in NG-GSP to the end. Okay, that notation looks a bit intimidating.
It is, yeah.
Can you remind us what it represents?
It simply represents the set of double causates formed by NGKE on the left, AG in the middle, and psi to the N on the right.
Got it. So Cohen finds a nice way to represent those double causates.
Yes. He shows that the representatives can be written in a specific form. TJSXYZ, where TJ is a diagonal matrix that depends on I and J.
Right.
And SXYZ is a specific matrix that depends on X, Y, and Z, which are elements of the maximal ideal P.
Okay, so those representatives have a specific structure.
They do.
What does he do with them?
He then uses a series of lemmas to refine these representatives, zeroing in on the conditions that determine whether or not a particular double causate belongs to SUP.
Right.
He analyzes those RG subgroups and demonstrates that under certain conditions, they either contain specific unipotent subgroups or can be transformed through a change of basis into specific forms.
Okay, so he's carefully sifting through those double causates, ruling out some and characterizing others.
Exactly.
Could you remind me what unipotent subgroups are?
Oh, yeah. So think of them as subgroups made up of matrices that are close to the identity matrix.
Okay.
Their entries differ from the identity matrix by elements of the maximal ideal P.
So they're like slightly perturbed versions of the identity matrix.
Exactly.
Okay.
And by using the properties of these unipotent subgroups, along with the fact that the representation is cuspidal, Cohen can eliminate certain double cossets from belonging to sup.
Okay, so it's a process of elimination.
Yeah,
He's ruling out certain double cossets based on their properties.
precisely.
And for those remaining double cossets,
Yes.
he shows that they can be conjugated, meaning transformed through a change of basis into specific forms that are crucial for his later calculations.
So it's like he's categorizing the double cossets that matter.
Exactly.
And the culmination of this categorization is summarized in Lemma 3.8, a key result in the paper.
It is.
Okay, what does Lemma 3.8 tell us? It provides a complete description of the double cossets belonging to sup.
Okay.
It tells us these double cossets can be classified into 5 distinct types, labeled as type 1, type 2, type 3, type 3, and type 4.
Okay.
And for each type, the lemma outlines the specific structure of the corresponding subgroup RG.
So now we have a clear picture of the double cossets that play a role in the dimension problem.
Yes.
What's the next step?
Well, now that we know which double cossets are important,
Yeah.
the next step is to actually count them.
Counting them. Why is that so important?
Remember to calculate the dimension of the space of Siegel vectors.
Right.
We need to sum the dimensions of Ceph restricted to RG over all double cossets in sup.
Right. So to compute that sum,
Yeah.
we need to know how many terms we're adding up.
Exactly. And that's precisely what Cohen does in section 4, titled Counting Double Cossets.
Okay, let's delve into section 4 and see how he tackles this counting problem.
Okay.
I'm assuming he uses those 5 double cosset types from Lemma 3.8.
He does. In section 4, Cohen embarks on the meticulous task of counting those double cossets.
Right.
And thanks to Lemma 3.8, we know that the relevant double cossets fall into those 5 types.
Right.
I, Pradar, the I bin 4.
Okay.
He cleverly uses the conditions he established in section 3, coupled with some detailed but straightforward matrix calculations to determine the exact number of double cossets of each type.
So it's like he's taking inventory of those 5 double cosset types.
Yeah.
Figuring out how many of each kind we have.
Exactly.
And he presents his findings in a series of lemmas.
Yes.
Lemma 4.1, Lemma 4.2, Lemma 4.3, Lemma 4.4, and Lemma 4.5. Each one dedicated to a specific type of double cosset.
It is a lot of lemmas.
The formulas he derives depend on N, which represents the level of the Siegel congruent subgroup,
Right.
and in some cases also on Q, the size of the residue field.
Right.
It sounds like this section is a bit technical with a lot of detailed calculations involved.
It is, yeah, but if you work through them, it's not too bad. The main takeaway is that Cohen successfully counts the double cossets in sup,
Right.
which is crucial for the next step, putting all the pieces together and unveiling those dimension formulas.
Okay, I'm ready for those formulas. Let's move on to section 5 and see what Cohen has in store for us.
Okay.
In section 5, titled Main Dimension Formulas, Cohen finally reveals the culmination of all that meticulous work.
Yeah.
Theorem 5.1, which presents those long-awaited dimension formulas.
Big reveal.
Okay, I'm on the edge of my seat. What do these formulas look like?
They're a bit intricate,
Okay.
but essentially they give us a precise way to calculate the dimension of the space of Siegel vectors for those specific non-generic depth 0 supercuspidal representations we've been focused on.
And I'm assuming those formulas depend on whether Q is odd or even.
You're absolutely right. Theorem 5.1 splits into 2 distinct cases.
Okay.
One for odd Q and one for even Q.
Right.
As you might expect, the formulas are quite different in these 2 cases, reflecting that fundamental dichotomy we've encountered before in number theory.
Okay, can you give us a sense of what these formulas look like?
Sure, for odd Q, the formula is relatively straightforward.
Okay.
It utilizes the floor function, which
Yeah.
essentially rounds a number down to the nearest integer,
Right.
and a term that hinges on whether the representation is equal to its twist by the Atkin-Lehner element.
Okay, so the odd Q formula is manageable.
Yeah.
What about the even Q formula? Is it more complicated?
It is a bit more involved.
Okay.
It involves a function, fnq, defined piecewise,
Okay.
meaning it has different expressions depending on the value of n.
Right.
This fnq function captures the complexities of the counting problem when q is even.
I see. So the even Q case introduces an additional layer of complexity.
Yeah, it does.
Does Cohen provide any specific examples to illustrate how these formulas work in practice?
He does, and the example he chooses is particularly fascinating because it links back to one of those unsolved problems in the classical theory of Siegel modular forms that we mentioned at the beginning.
Oh, cool. You mean the dimensions of those spaces of cusp forms for Siegel congruence subgroups?
Exactly. Cohen delves into the special case where f equals q2, the field of two adic numbers.
Okay.
He demonstrates that in this case, the formulas from theorem 5.1 simplify considerably, offering a more concrete path to calculate those elusive dimensions.
Okay, so this special case provides a nice concrete illustration of how the general theory plays out.
It does.
And the results are summarized in corollary 5.2,
Yes.
which presents that simplified dimension formula for f equals q2.
Right.
What's really intriguing is that the dimensions in this case form a sequence of numbers with a curious pattern
Yeah.
that mathematicians are still trying to fully unravel.
It's a really interesting sequence.
Wow, so even this special case leads to some tantalizing open questions.
Yeah.
It seems like we've only just scratched the surface of this rich mathematical landscape.
I know, there's so much more to explore.
Well, I'm definitely feeling inspired to explore further. But before we get lost in contemplation,
Wow.
let's return to that other key player in this story,
Okay.
the Aitken-Lehner involution.
Right.
We've talked about its role in identifying double cosets and mentioned its signature,
Uh-huh.
but we haven't explored that signature in detail yet.
Yeah.
What's next on our agenda?
In section 6, aptly titled The Aitken-Lehner Involution,
Oh,
Cohen digs deeper into the signature of this intriguing involution,
yeah.
analyzing how it acts on those spaces of Siegel vectors.
Right.
This analysis provides crucial information for understanding the structure of these spaces
Okay.
and their connections to other areas of mathematics.
Okay, I'm ready to unravel the mysteries of this signature.
Uh-oh.
But it looks like we've reached the end of our time for this segment.
Okay.
We'll continue our deep dive into this fascinating paper in part 3 of this episode.
Sounds good.
Until then, keep those mathematical gears turning.
I will.
So welcome back to our deep dive into Jonathan Cohen's fascinating paper. We've explored this intricate world of Siegel vectors and double cosets and character table calculations.
Right.
And we even uncovered some secrets about the Aitken-Lehner involution.
Yeah, that was cool.
Now it's time to confront the signature of this mysterious involution head-on.
Let's do it.
So, to calculate the signature,
yeah.
we need to understand how the Aitken-Lehner involution acts on each double coset in sup.
Right.
And then we need to determine the trace of the corresponding operator on the space of restricted to RG.
Exactly.
Okay, so those traces hold the key to unlocking the signature.
They do.
How does Cohen approach this challenge?
He begins with lemma 6.1,
Okay.
a technical but crucial result that analyzes how the Aitken-Lehner element, un, acts on each type of double coset representative.
Okay.
Remember, we classified those double cosets into 5 types earlier.
Right, types un, 2, 3 up, 3, and 4.
Yeah.
Each with its own special characteristics.
Exact.
How does un behave when it encounters these different types?
Okay, so lemma 6.1 reveals that for certain types, un simply permutes the double cosets within that type.
Okay.
For example,
Yeah.
if G equals tie A represents a type I double coset, then gun is another type I double coset.
Okay.
And the lemma provides a formula relating the indices I and J of these two cosets.
So it's like unlemma is rearranging the furniture within certain rooms.
Yes, that's a good way to put it.
While leaving other rooms untouched.
Exactly.
And for other types of double coset,
Yeah.
un's action is a bit more complex.
Yeah, it can be.
Involving both permutation and twisting by elements of NGKP twisting. Can you unpack that for us?
So twisting a representation involves modifying it by composing it with an automorphism of the group. In this case, those automorphisms are given by conjugation with elements of NGKP.
Okay, so un can induce these twists, adding another layer of complexity to its action.
Yeah, it does.
What's the main takeaway from lemma 6.1?
Lemma 6.1 equips us with a clear understanding of how the Aitken-Lehner element operates on each type of double coset. This knowledge is essential for calculating the signature.
So we're one step closer to that signature formula.
We are.
Where does Cohen reveal this crucial formula?
The formula itself is presented in Theorem 6.2,
Okay.
another key result in the paper.
Right.
As expected, it's a bit intricate.
Okay.
Splitting into several cases based on whether n is even or odd and whether q is even or odd.
Right.
The formula combines combinatorial terms and character values,
Yeah.
reflecting the complexity of the Aitken-Leonard involution's action.
It sounds like a masterpiece of mathematical precision,
It is.
capturing all the subtle nuances of the involution's behavior.
It really does.
Does Cohen offer any concrete examples to illuminate this intricate formula?
He does.
Okay.
He revisits the special case where f equals q2 and examines the two possible extensions of the unique irreducible cuspidal representation of GL2 to NGKP.
Right.
In this case, the signature formula simplifies beautifully,
Okay.
offering a more tangible way to grasp the signature.
So once again, this special case provides a grounding point,
Yes.
allowing us to see the abstract theory in action.
Right.
Where can we find this simplified signature formula?
It's presented in Corollary 6.3.
Amazing. It feels like we've climbed a mathematical mountain
Yeah,
and now stand at the peak,
it does.
surveying the vast landscape of Cohen's work.
It's a beautiful view from up here.
And from this vantage point, we can see the connections between seemingly disparate concepts: Siegel vectors, double cosets, character tables, and the Aitken-Leonard involution,
They all come together.
all woven together to illuminate this deep problem in number theory.
It's really elegant.
This deep dive has been a truly enlightening experience.
It has.
Cohen's work showcases the power of abstract mathematics to tackle concrete problems,
Yeah, it's a great example of that.
and reminding us that even in the most technical and intricate realms, beauty and insight can be found.
Absolutely.
Well, on that inspiring note, we've reached the end of our deep dive into Jonathan Cohen's groundbreaking paper.
It was a good one.
Thank you for joining us on this mathematical adventure, and until next time, keep exploring the infinite depths of mathematical knowledge.
Keep exploring.
Welcome back, everyone. Today's deep dive is going to be a wild one. We're tackling a paper on Siegel vectors for, those are non-generic depth, zero supercuspidal representations of GSp4.
Oh, yeah. This is a fun one.
So buckle up, everyone, because we're going deep into some serious mathematics.
Yeah, and what makes this paper even more fascinating is that it actually connects to a problem that has its roots in like classical theory of Siegel modular forms.
Oh, really?
Yeah, so determining the dimension of spaces of Siegel modular forms, particularly cusp forms, has been a fundamental problem in number theory for a long time.
Right, it's like trying to figure out the size and shape of this, like, complex mathematical structure. Right?
Exactly. And recently there's been some really cool progress in calculating these dimensions, especially for what's known as the clinging congruence subgroup of level 4.
Okay, I've heard of that.
Yeah, and that research, was published in 2022, laid a lot of the foundation for the paper we're looking at today.
Okay, so like building on previous work.
Yeah, a key insight from that earlier work was the crucial role played by the dimensions of certain fixed vector spaces within irreducible smooth representations of GSp4 Q2.
Okay, so this new paper is taking a similar approach, but focusing on a different family of subgroups, the Siegel congruence subgroups of level P to the N.
Right, and these subgroups, they can be represented by matrices with specific entries that belong to the p-adic integers denoted ZP.
Z, okay.
But instead of trying to tackle all representations of GSp4 at once, the authors strategically focus on a particular type.
Makes sense. Going to narrow it down somehow, right?
Yeah, exactly. They focus on what are called depth 0 supercuspidal representations.
Okay, so why focus on those specific representations?
Well, depth 0 supercuspidals are known to be both interesting and manageable in a sense. They're the building blocks for more complicated representations.
Okay, so start with the basics and build up from there.
Exactly. And what's really cool is that this paper unveils a surprising dichotomy. The behavior of these representations seems to split depending on whether the prime number p is equal to 2 or greater than 2.
Oh, wow. So like two different mathematical universes.
It really is like that. It's almost as if different rules govern those two cases.
Fascinating. And as if that wasn't enough complexity, the paper also explores how the Aitken-Leonard involution, which is kind of like a symmetry operation, affects the space of Siegel invariant vectors.
Yeah, the Aitken-Leonard involution is super important in this context. It adds like another layer of structure that we need to understand.
Okay, well, it sounds like we've got a lot to unpack.
We do.
Let's start with section 2. where the authors set the stage and introduce a bunch of key definitions and notations.
Sounds good.
So first up, we have the field F, which is a finite extension of the p-adic numbers QP.
Right. F is our base field, and it comes with a whole bunch of associated structures. Its ring of integers denoted its maximal ideal PF, a special element called a uniformizer, usually denoted F, and the residue field FQ.
Okay, so a lot of moving parts already. And what about that parameter E?
Yes. E. It takes the value 1 if F is ramified over Q2 and O if it's unramified.
Ramified versus unramified.
Yeah, this parameter might seem like a minor detail, but it plays a subtle but important role later on.
Okay, so we got to keep an eye on E.
Definitely. Now let's talk about the main player, the group GSp4F. It's defined as the set of all invertible 4x4 matrices over F that preserve a specific alternating form up to a scalar.
Okay, 4x4 matrices, I can picture those.
Good. And the key property of these matrices is that when you multiply a matrix G in GSp4F by its transpose, and then by a fixed matrix J, you get a scalar multiple of G.
So they preserve this matrix J in a way.
Yeah, they scale it but keep its essential structure intact. This scalar is denoted by G, by the way.
Got it. And then there's that other group, GL22TQ, which consists of pairs of 2x2 matrices where the determinants have to be equal.
Right. It's a group of matrix pairs. GL22Q is important because it will help us connect with the representation theory of smaller groups.
Okay, so we're starting to see how these different groups will come into play.
Exactly. Now we're going to introduce a whole bunch of subgroups, each with its own special role to play.
Bring it on. Some groups are fun.
They are. First, we have Z, the center of our group GSp4F. It consists of all the scalar matrices.
Okay, the center, that's where everything commutes, right?
Yep. Then there's T, the set of all diagonal matrices in GSp4F.
Diagonal matrices, those are pretty easy to work with.
They are. And then we have G0, the set of matrices in GSp4F, whose G, remember that scalar factor has a p-adic valuation of at least 0.
Also, those are the well-behaved matrices.
You could say that. Their scaling factor isn't too wild in the p-adic world.
Okay, what's next in our parade of subgroups?
Next up are two maximal compact subgroups, K and KP, both living inside GSp4F. These guys are crucial for constructing the representations we'll be exploring.
Maximal compact subgroups, those sound important.
They are. And let's not forget the Iahori subgroup, denoted by I. It's another key player. It consists of matrices that are upper triangular modulo P.
Modulo P. Okay, so we're starting to see that modular arithmetic coming in.
Exactly. And finally, we arrive at the stars of the show, the Siegel congruence subgroups.
Ooh, the main attraction.
They are. They're denoted by SOLI-Pn for each positive integer n. You can think of them as sets of matrices that are congruent to the identity matrix modulo Pn in a specific way.
Okay, so they're like increasingly fine-grained filters on our matrix space as n gets larger.
That's a great way to put it.
So we have all these subgroups, each with their own personality.
Yeah.
But how do they all fit together? It seems like a lot to keep track of.
Don't worry, it'll all come together beautifully. The authors provide this really helpful isomorphism between KP, KP+, and GL2Q.
Okay, so a connection between those two groups.
Exactly. It essentially maps matrices in KP to their upper left 2x2 blocks modulo P.
So we're connecting our larger matrices in GSp4F to the world of 2x2 matrices.
You got it. And this connection is super useful because it allows us to translate information back and forth between those two worlds.
That's clever. Okay, what else do we need to know?
Well, there's this compact notation for representing restrictions of tensor product representations. If you have two representations, one in Jirta of GL2Q, the restriction to GL2Q is denoted by this, 1 Q.
Okay, so it's a shorthand for those restrictions.
Exactly. And this notation is really handy because every irreducible representation of GL2Q can be found as a subrepresentation of some 1 or 2.
Oh, so it's like a way of capturing the relationships between these representations.
You got it. Now we're going to introduce some special matrices, S1, S2, and UN.
Special matrices.
Yeah. So the matrices S1 and S2 are simple 2x2 matrices. Their images actually generate the Weil group W.
The Weil group.
Yep. It's a group that captures certain symmetries within our matrix groups. And then we have UN, the Aitken-Lehner element.
Ah, that sounds familiar.
It should. It depends on the integer n, and it plays a key role in understanding the signature of the Aitken-Lehner involution, which we'll encounter later on.
Okay, so UN is like holding a key to some hidden mathematical pattern.
I like that analogy. Now let's talk about central characters.
Central characters.
Yeah. They're denoted by us. Essentially, they tell us how a representation acts on the center of a group.
Okay, so like a fingerprint for the representation.
Exactly. They help us distinguish between different representations. They're particularly useful when dealing with induced representations, which is what we'll be doing a lot of in this paper.
Induced representations, those are where you build representations of a larger group from representations of a smaller group, right?
You're exactly right. And the authors use a specific type of induced representation called compact induction, denoted by C and DGH. It's a powerful tool for constructing representations.
Like taking a blueprint for a small room and using it to build a whole house.
That's a great way to think about it. Now we're finally getting to the heart of the matter depth, zero supercuspidal representations of GSp4.
The stars of the show.
Yes. As the paper explains, these representations can arise in two ways, either through compact induction from the subgroup ZK or from the normalizer of KH.
So two different construction methods.
Yeah. In both cases, we start with an irreducible cuspidal representation of a smaller group and then use compact induction to lift it to a representation of GSp4.
Like building a complex molecule from simpler atoms.
Precisely. But for this paper, the authors choose to focus on the second case, where the representations arise from the normalizer of Kp.
Okay, so they're leaving the other case for future research.
Exactly. And importantly, they mention that non-generic representations arising from K have no fixed vectors for any n.
Oh, so that simplifies things a bit.
Yeah, it means by focusing on representations coming from the normalizer of Kp, we're actually covering all the interesting cases for Siegel vectors.
Okay, so we've narrowed down our focus even further.
Yep. So to sum up, Section 2 has given us a comprehensive toolbox full of definitions, notations, and crucial concepts.
We're well equipped for the journey ahead.
We are. Now let's move on to Section 3, where the real action begins. This is where we delve into the world of Siegel vectors.
I'm ready for it.
Good. It all starts with a specific formula, the dimension of psi pn, that is, the space of vectors fixed by the action of the Siegel congruent subgroup in the representation, is given by a sum of dimensions of certain spaces denoted by psi. And this sum is taken over a special set called the supportive, denoted as sup.
Okay, formula. And what's this sup all about?
Sup consists of double causates. These are sets of the form NGK ECSI for specific elements G in GSp4f where sup is non-zero. Think of them as equivalence classes that capture how the group NGKP acts on GSp4f.
Okay, equivalence classes. Got it.
So the strategy is to figure out what this set sup is and then calculate the dimension of size for each double causate representative G in sup.
Yeah.
It's like breaking down a complex problem into smaller, more manageable pieces.
Divide and conquer. I like it.
Yeah.
So where do we even begin?
Well, the authors take us on a little detour into the world of character tables in section 3.1.
Character tables, huh? Those tables that tell us about the traces of representations, right?
You're exactly right. Section 3.1 kicks off with Remark 3.1, which highlights an important condition for a compactly induced representation to have Siegel vectors. The central character of the corresponding representation of Kp plus must be trivial on the image of ZKP.
Okay, so there's like a secret handshake the representation needs to do to get into the club of Siegel vectors.
I like that analogy. And Lemma 3.2 reveals that the representations we're interested in do indeed have this secret handshake. It uses character tables to calculate the dimensions dims R for various subgroups R.
Okay, so we're using those character tables to get concrete numbers.
Yes, and Lemma 3.2 carefully examines different cases depending on whether Q is even or odd. It really lays out a detailed roadmap for calculating those dimensions.
Roadmap, excellent.
Yeah.
So why is this lemma so important?
Well, it gives us the tools to actually calculate the dimensions of those fixed spaces that appear in our main dimension formula.
Okay, so it's a crucial stepping stone.
Exactly. But before we can apply those tools, we need to figure out exactly which double causates belong to sup.
Right, we need to know what we're dealing with.
Exactly, and that's what section 3.2 is all about. It's like a detective story where we're gathering clues to solve a mathematical mystery.
I'm intrigued. How do we start gathering those clues?
The authors cleverly utilize a well-known decomposition, G, ING, TI. This tells us that our group G can be built from the Iwahori subgroup I and the normalizer of the diagonal matrices NGT.
Oh, so we're breaking down this complex group into simpler building blocks.
You got it. And this decomposition, combined with what's known as the Iwahori factorization, allows us to choose representatives for the double causates in NGJPN in a very specific form, TIJSXYZ.
TIJSXYZ. Okay, and what are those T and S things?
Well, TIS3 is a diagonal matrix with entries that depend on the uniformizer and the indices INJ.
Okay, diagonal matrices, those are usually nice.
They are. And SXYZ is a more complicated matrix matrix, but it involves these variables x, y, and z.
Variables. Okay, so things are getting a bit more abstract.
A little bit. But we can actually impose some constraints on those variables and on the indices I and g.
Constraints. How so?
Well, based on relations that come from manipulating these double cosets, we can deduce some restrictions on the p-adic valuations of x, y, and z, and also on the possible values of I and j.
Okay, so we're narrowing down the possibilities.
Exactly, and lemma 3.5 provides even further constraints on the p-adic valuations of those variables. It's all about using the structure of those matrices and the properties of p-adic valuations to eliminate unnecessary cases.
Like we're trimming the fat.
That's a great way to put it. Now, there are two special subgroups within GL2Q denoted U1 and U2.
U1 and U2, more subgroups.
Yes. And lemma 3.6 tells us that if RG contains either of these subgroups, then the space is 0. This is a really crucial observation.
Why is it so crucial?
Well, it comes from the cuspidality of speces. Remember that cuspidality imposes strong constraints on the representation.
Ah, right. So it's like a rule that eliminates certain possibilities.
Precisely. And then we have lemma 3.7, which offers a helpful simplification by focusing on the Siegel-Levi subgroup denoted by M.
The Siegel-Levi subgroup, what's that?
It's another subgroup. But this lemma tells us that if a double cos G belongs to sup, we can actually just work with its intersection with M without losing any information.
Oh, so it's like we can zoom in on a specific region without losing sight of the big picture.
Exactly. It's a great example of how we can exploit the structure of these groups to simplify things.
Love it. Okay, so we're getting closer and closer to understanding sup.
We are.
Yeah.
And finally, we arrive at lemma 3.8, which brings all the pieces together. It tells us exactly which double cosets belong to sup.
So the climax of section 3.
You could say that. Lemma 3.8 gives us the necessary and sufficient conditions for a double coset to be in sup, and these conditions involve the indices I and j, valuations of x, y, and z, and of course the distinction between q even and q odd.
So it's like the culmination of all our hard work in this section. We've finally identified the key players.
Exactly. And lemma 3.8 is the key to unlocking the next stage of our adventure, which is counting those double cosets in sup.
Ooh, that sounds exciting.
It is. Get ready for some really neat formulas and some surprising connections to geometry.
Can't wait.
All right, so we've laid the groundwork, identified the key players, and narrowed down the possibilities for our double cosets.
Yeah, lots set up.
Now, section 4 takes us deep into the world of counting those double cosets in sup.
Okay, counting time.
This is where things get really interesting because the number of these double cosets directly contributes to the dimension formula we're ultimately aiming for.
Right, like we've gathered all the pieces of the puzzle, and now we're figuring out how they fit together.
Exactly. But before we jump into the specific lemmas, is there a general strategy we can use for counting these double cosets?
Well, I remember we categorized the double cosets into those 5 types, right?
You have a great memory.
Oh.
And that categorization is key. Each double coset uniquely determines the subgroup RG, at least up to conjugation.
Ah, so no overlap between double cosets of different types.
Precisely. So we can count each type separately and then add up the results to get the total count.
Okay, that makes sense. Divide and conquer.
And that's exactly what the authors do in this section. Combining this idea with lemmas 3.7 and 3.8 allows us to count each type of double coset on its own.
Perfect. So let's dive into the lemmas and see how they tackle these counts.
Okay. Lemma 4.1 gives us the count for type I double cosets, and it's a remarkably concise formula. 24.
Wow, that's pretty elegant. But I'm a little confused about the floor function. What's that doing there?
Ah, yes, the floor function. It essentially rounds a number down to the nearest integer. So if you have like 3.7, the floor function of that would be 3.
Okay, rounding down makes sense. So how do we get to this formula for the type I double cosets?
Well, remember that type I double cosets are represented by Tij, where I and j are those integers satisfying certain conditions. The key is that each distinct pair, Ij, gives us a unique double coset.
Okay, but there are infinitely many integers, so how do we end up with a finite count?
That's where those conditions on I and j come in. They actually define a bounded region in the Ij plane.
Bounded region, what does that look like?
If you plot those inequalities area in one area and one area and one area, you'll see that the region they define is essentially a triangle.
A triangle.
Yes, so we're essentially counting the number of points with integer coordinates, the lattice points that fall within this triangle.
Oh, I see. So it's a geometry problem in disguise.
Exactly. And it turns out there's a nice formula for counting the number of lattice points within a right triangle like this, and that's where that formula 24 comes from.
Wow, that's so cool. So we're using geometry to solve this algebraic problem.
It's a beautiful connection between different areas of math. Okay, so we've tackled type I double cosets. What about type 2?
Bring it on.
Lemma 4.2 handles that case. And remember, type 2 double cosets only pop up when Q is even and N is at least 4.
Right. I remember that distinction.
Good. The formula here is a 24-year, and the reasoning is very similar to the type I case.
So are we counting lattice points in a triangle again?
You bet. Type 2 double cosets have the form TIJS000, but now we have that extra condition, val(xi plus j.
Ah, right, that valuation condition.
Exactly. Combining that with the other constraints from lemma 3.6 gives us another triangular region in the IJ plane.
Another triangle. I'm starting to think triangles are the key to this whole thing.
Well, they certainly play a big role. And just like before, we can use the geometry of this triangle to derive that formula for the number of type 2 double cosets.
Awesome. Okay, so we've handled type I and type 2, both with nice geometric interpretations.
Mm-hmm.
What about types the III and II? Those seemed a bit more complicated.
You're right. Those are a bit trickier. Lemmas 4.3 and 4.4 deal with those cases. And remember, they involve that extra parameter, and we need to deal with squares in the residue field.
Yeah, squares modulo Q.
Exactly. So instead of just counting pairs, IJ, we're now dealing with quadruples, IJ, RU, where U is considered modulo squares in a specific coset space.
Okay, quadruples, things are definitely getting more complex.
They are. But the authors show that these quadruples essentially determine the double cosets. And by carefully analyzing the conditions on these quadruples, they derive formulas for the number of distinct double cosets of types, IFIA and IIR.
Can you give me a sense of what those formulas look like?
Sure. They involve sums over different values of I, J, and R, and they include a factor of Q raised to a power that depends on J and R.
Q, the size of the residue field.
That's right. The presence of Q in these formulas reflects the fact that we're working modulo squares in the residue field.
Makes sense. So even though the formulas are more complicated, we can still see how they're built from the structure of these double cosets.
Exactly. It's all very carefully laid out, and it all comes back to those conditions on the quadruples.
Cool. Okay, so what about type IV double cosets?
Ah, yes. Lemma 4.5 tackles those. And similar to type 2, these only exist when Q is even and N is sufficiently large. The formula here is Q1.
Q124. It looks a bit like the formula for type 2, but with that extra Q1 factor. You're very observant. The type IV double cosets involve some of the most intricate conditions. We end up considering double cosets of the form TI psi hui plus J1, where U is now considered modulo P, not modulo squares like in the type 3 cases.
Oh, interesting. So the space we're working in has shifted again.
Precisely. And that shift is reflected in the formula through that factor of Q1.
So that's where it comes from. And the 24 part. Another triangle.
You guessed it. It comes from counting the pairs, IJ, that satisfy the relevant inequalities. And those inequalities, again, define a triangular region in the IJ plane.
Triangles everywhere. It's amazing how they keep popping up even in this very abstract setting.
It really highlights those deep connections between geometry and algebra.
Okay, so we've meticulously counted all the different types of double cosets that contribute to SUP. What's next?
Now we're finally ready to tackle those dimension formulas themselves in Section 5. This is where we reap the rewards of all our hard work.
The moment we've all been waiting for. It is. And Theorem 5.1 is a star of this section. It presents those dimension formulas, and as we've seen before, it distinguishes between the cases of Q odd and Q even.
Right, that dichotomy seems to be a recurring theme in this paper.
Well,
why is this distinction so important in the context of the dimension formula?
Well, it stems from the inherent differences in the structures of the groups involved and the behavior of the representations when Q is even versus when it's odd. When Q is odd, we can actually leverage the fact that certain fixed spaces have dimension 0, which simplifies the calculation significantly.
So when Q is odd, the only contributions come from those diagonal double cosets, leading to a nice clean formula.
You got it. But when Q is even, the situation is much more intricate. We need to take into account all those different types of double cosets, which leads to a more complex formula involving a new function.
FNQ.
Okay, FNQ, new function alert. What does this function do? FNQ is essentially encapsulating all the complexity of the even Q case. It captures how the dimensions of those fixed spaces associated with each type of double coset combine to determine the overall dimension of the space of Siegel vectors.
So it's like a master accounting tool keeping track of all the contributions.
Exactly. And while Theorem 5.1 doesn't give us an explicit formula for FNQ, it assures us that it can be calculated based on the results we've already seen.
That's reassuring. So theorem 5.1 gives us the general dimension formula, but then corollary 5.2 gives a specific formula for the case where F is Q2, where the residue field is F2. This formula seems much simpler than the general case for even Q. Why is that?
The simplification happens because the residue field F2 is incredibly small, containing only two elements, 0 and 1. This significantly reduces the number of possibilities we need to consider when counting those double cossets and calculating the dimensions of the fixed spaces.
Oh, I see. So it's like specializing to a smaller, simpler case allows us to see the structure more clearly.
That's a great insight. Sometimes narrowing our focus can actually lead to deeper understanding.
I like that. Okay, so we've got those dimension formulas all sorted out. What's next in this mathematical adventure?
Well, the paper doesn't stop there. Section 6 introduces a new twist by exploring the Aitken-Lehner involution and its effect on those spaces of Siegel vectors.
The Aitken-Lehner involution. Ah, yes. I knew it would make it come back. So we're not just looking at dimensions anymore. We're looking at how this involution might transform the space.
Precisely. Instead of just focusing on dimensions, we're going to examine the signature of the Aitken-Lehner involution on the space of Siegel vectors.
Signature. Okay, so what does that tell us?
It tells us how many vectors in the space of Siegel vectors are fixed by the Aitken-Lehner involution and how many change sign under its action.
Ah, so like we're categorizing those vectors based on how they respond to this involution.
Exactly. And to analyze this signature, we're going to rely heavily on Table 1 again. Remember that handy table that summarizes all the key properties of our 5 types of double cossets?
Oh yeah, that table is super helpful. So we're using it to understand the Aitken-Lehner involution now.
We are. It provides crucial information about how the Aitken-Lehner element acts on representatives of each type of double cosset. Then lemma 6.1 delves into the specifics of how the Aitken-Lehner element acts on functions in the representation space.
Okay, so it's like a close-up view of the action.
Exactly. It breaks down the action for each of the 4 types of double cossets, and it's crucial for understanding those fixed points of the Aitken-Lehner involution.
Got it. So lemma 6.1 gives us a handle on how the Aitken-Lehner element acts. What happens next?
Then comes theorem 6.2, which unveils the signature denoted as phin of the Aitken-Lehner involution on the space of Siegel vectors.
Okay, signature reveal. And does this theorem also distinguish between the cases of even and odd n?
You bet it does. That even-odd distinction pops up again and again in this paper.
So what's the difference between those cases when it comes to the signature?
When n is even, the action of the Aitken-Lehner element is a bit simpler. It either preserves a double cosset or sends it to another double cosset of the same type.
So things are a bit more predictable.
You could say that. But when n is odd, things get more intricate.
Oh no. What happens when n is odd?
The action of the Aitken-Lehner element can now involve the representation, and that can introduce a sign change which we need to carefully account for.
Sign change. That sounds tricky.
It is, and the sign change depends on how U1 acts on, leading to those more complicated formulas in theorem 6.2 for the odd n case.
Okay, so even n is more straightforward. Odd requires more careful analysis. I'm sensing a pattern here.
You're absolutely right. And just like with the dimension formula, corollary 6.3 gives us a specific signature formula for the case when F equals Q2.
Q2 to the rescue again.
It seems like specializing to Q2 often simplifies things.
Yeah, it's like Q2 has a special connection to this problem.
It does seem that way. Anyway, with that, we've covered the main results of Section 6.
The Aitken-Lehner involution and its signature all laid out.
Yes. But the paper doesn't end there. There's still one more important piece of the puzzle that we need to revisit.
Oh, really? What have we missed?
We need to go back and take a closer look at the proof of lemma 3.2. Remember that lemma that established the dimensions of certain fixed spaces within the representation?
Oh, right. Lemma 3.2. I remember it involved a lot of calculations with character tables.
You've got it. Those dimensions are absolutely crucial for calculating the overall dimension of the space of Siegel vectors. So we need to understand how they're derived.
Okay, so back to character tables we go.
Exactly. And the proof of lemma 3.2 relies heavily on the character table of GL2Q, which acts like a dictionary that tells us how representations behave.
Ah, yes. Character tables. They're like a secret code that we need to decipher.
That's a great way to think about it.
Yeah.
So are you ready to dive into the details of this proof?
Absolutely. Bring on those character tables.
Okay, so lemma 3.2, it's got 4 parts, right?
Yeah, A, B, C, and D.
Right, and each part deals with calculating the dimension of psi r for a different subgroup R. But the overall strategy is the same in each case.
Okay, and what's that strategy?
Well, it involves using the character table of GL2Q and exploiting the cuspidality of the representation spec.
Ah, right. Cuspidality. That
Yeah.
seems to be the key to a lot of the simplifications in this paper.
You're absolutely right. Cuspidality imposes these strong constraints on the character values of SA, which really helps us narrow things down.
Okay, so let's start with part A of Lemma 3.2. What's the setup there?
So in part A, we're considering the representation SA1 year 2, where 1 and rig are irreducible cuspidal representations of GL2Q.
Okay, tensor product of two smaller representations.
Exactly. And there's this additional condition that their central characters have to multiply to 1. Remember those central characters?
They're like fingerprints for the representations, right?
You got it. So we have this specific type of representation, and the subgroup R, in this case, consists of pairs of matrices with a specific form. They look like this, ABC, ABC1, where A, B, and C are non-zero elements of the residue field, FQ.
Okay, so a very particular family of matrices. And what are we trying to calculate?
We want to find the dimension of R, the space of vectors yin that are fixed by the action of all the elements in R.
Ah, the fixed space. Okay, and how do we do that?
Well, we use the character formula. Remember, that tells us that the dimension of R is equal to the average of the trace of tan G over all elements G in R.
The character formula. Traced average, all that good stuff. Okay, so how do we actually compute this average trace?
Well, since Pons is a tensor product representation, the trace of EG for an element G equals G1, G2 in R is just the product of the traces of R1, G1 and of FER G2.
So it's like the trace of the big representation is built from the traces of the smaller ones.
Exactly. And here's where cuspidality comes in. The cuspidality of 1 and R2 means that their character values, which are essentially the traces, are 0 on a lot of elements of GL2Q, specifically those that aren't scalar matrices.
Oh, so cuspidality is really helping us out here, at eliminating a bunch of potential terms in that average.
Exactly. The only elements in R that actually contribute to the trace are those of the form, AI2, AI2, where I2 is the 2x2 identity matrix.
Okay, so just those scalar matrix pairs.
Yes. And when Q is odd, we also need to consider the pairs. AI2 and HAI2.
Why just when Q is odd?
Well, because when Q is even matter 1 is actually the same as 1 in the residue field FQ. So those pairs would be the same as the ones we've already counted.
Ah, right. Modular arithmetic.
Ah.
Okay, so we've significantly reduced the number of elements we need to worry about. What are the character values on these special elements?
Well, the character value on AI2 is just the product of the dimensions of 1 and 2, which is Q12, multiplied by the value of the central character fuss on A.
Okay, and what about that central character value?
Well, remember that the central characters of 1 and 2 multiply to 1, so hus A is also equal to 1.
So it simplifies nicely.
Yeah.
What about the character value on AI2 NaNH AI2 when Q is odd?
That one is Q12 multiplied by usi A, which simplifies to damus 1, again, because the central characters multiply to 1.
Okay, so we have all the pieces we need to calculate the dimension of SA. It's just a matter of averaging those character values over all the possible values of a pus in FQ.
Precisely. And when you do that averaging carefully, you find that the dimension is 1 plus U, oneness is 1 when Q is odd, and just 1 when Q is even.
So that's part A of Lemma 3.2 all wrapped up.
Yes. It's a beautiful example of how we can use character tables and the properties of cuspidal representations to calculate those dimensions explicitly.
Okay, so what about part B?
Part B is similar in spirit, but the subgroup R is a little different, and the representations 1 and O2 have to satisfy a specific property. Their restrictions to SL2Q have to be reducible.
Reducible meaning they decompose into a direct sum of smaller representations.
Exactly. And this condition of being reducible when restricted to SL2Q actually only happens when Q is odd. So part B is all about the odd Q case.
Okay, odd Q only. And how does the proof work?
Well, it uses the character table of SL2Q and the specific form of the elements in R to carefully calculate the trace of is on elements of R. And once again, cuspidality simplifies things a lot because a lot of those character values end up being 0.
Cuspidality is simplification superhero.
It really is. And after all those calculations, you get a nice formula for the dimension of SAR in this case.
Awesome. And what about parts C and D?
Parts C and D involve subgroups R with slightly different forms, but the core strategy remains the same. We analyze the elements of R, use the character table of GL2Q, and exploit the cuspidality of the representations to determine the dimension of R.
Okay, so it's the same dance, but with slightly different partners.
Exactly. The details change, but the underlying principles are the same.
Got it. So that wraps up Lemma 3.2 and its proof. We've seen how character tables and cuspidality are our best friends when it comes to calculating these dimensions.
Couldn't have said it better myself. Now are you ready to move on to Lemma 3.5?
Absolutely. bring on those p-adic valuations.
Okay, so lemma 3.5 is all about those double posits in sup, and it puts some important constraints on the valuations of those variables, x, y, and z, that appear in the double posit representatives. Remember those Tij, S, X, Y, Z thing?
Yeah, I remember those. They were getting a bit unwieldy.
They were. But lemma 3.5 helps us tame them a bit. So part A of the lemma says that if x is non-zero, then we can assume that I plus val yx is greater than or equal to 0.
That seems like a pretty technical condition. Why is that important?
It might seem technical, but it actually has a really nice geometric interpretation.
Ooh, I love a good geometric interpretation. What is it?
Well, you can think of the double coset Tij, S, X, Y, Z as representing a point in a certain space.
Okay, a point in space.
Right. And this condition, I plus val x 0, basically restricts us to a specific region within that space. It's like shining a spotlight on a particular part of the mathematical landscape.
Okay, so we're focusing our attention.
Precisely. And the proof of this part of the lemma uses a technique called conjugation. We can conjugate our double coset representative by a specific matrix without actually changing the double coset itself.
Conjugation, so it's like changing our perspective without changing the underlying object.
Exactly. And by choosing this conjugating matrix carefully, we can essentially move our point within that space.
Oh, so it's like we're manipulating our viewpoint to get a better look at things.
That's a great way to put it. And the proof shows that if we start with a double coset representative that doesn't satisfy that condition, I plus volley x, or O is 0, we can always conjugate it by a suitable matrix to get a representative that does satisfy the condition.
So we're not losing any generality by imposing that condition.
Exactly. It's a clever way to simplify our analysis without sacrificing any mathematical rigor.
Love it. Okay, what about part B of lemma 3.5?
Part B focuses on the case where x, y, and z are all non-zero and the valuation of z is equal to 2i plus 1 plus the valuation of y. In this case, we can further assume that I plus val x is less than or equal to 1. Remember E, that parameter related to the ramification of f over q2?
Oh yeah, E. It's back.
It is. And this part of the lemma is all about refining our understanding of those possible double cosets when those conditions on the valuations hold.
So it's like we're adding another layer of constraint.
Precisely. And the proof, again, uses conjugation, but with a different matrix this time. The condition on the valuation of z and the properties of p-adic valuations guide the choice of this conjugating matrix, leading to that inequality involving E.
Okay, so we're really using those p-adic valuations to our advantage here.
We are. They're incredibly powerful tools for understanding the structure of these double cosets. Now, are you ready for lemma 3.6?
Hit me with it.
All right. Lemma 3.6 dives even deeper into the structure of sup. It imposes even more specific conditions on the indices I and j, as well as the valuations of x, y, and z for a double cost to belong to sup.
So it's like we're tightening the net, closing in on the exact double cosets that we need to consider.
That's a great way to put it. And these conditions come from analyzing the subgroup RG associated with each double coset. Remember those RG subgroups?
Yeah, they're the ones that show up in that big dimension formula.
Exactly. And the cuspidality of sup is crucial here because it forces certain entries in the character table to be 0, which in turn imposes restrictions on the structure of RG.
Right, cuspidality shaping the landscape once again. So what are some of those specific conditions that lemma 3.6 gives us?
Well, part A of the lemma says that the index j has to be between 1 and n2 2i. This condition comes from considering the action of certain elements in the Siegel congruence subgroup, CPPN, and making sure that RG doesn't contain those special subgroups U1 and U2 that we talked about earlier.
Ah, right, those subgroups that would cause to be 0.
Exactly. So this condition on J is ensuring that we're only dealing with double cosets that can actually contribute to the dimension we're trying to calculate.
Makes sense. Got to eliminate those dead ends.
And then part B of lemma 3.6 says that we can assume that the valuations of by2 and y2 are bounded below by certain expressions involving I and j.
Bounded below. Okay. And where do those bounds come from?
They also come from considerations involving those subgroups U1 and U2 and the cuspidality of sup. The proof carefully analyzes the action of certain matrices in CPN on the double coset representative and shows that if those bounds aren't satisfied, then RG would have to contain either U1 or U2.
Ah, so it's another clever argument by contradiction.
Exactly. And then part C of lemma 3.6, which is particularly interesting, says that we can assume the valuation of z is precisely 2i plus 1 plus the valuation of y.
Okay, so a very specific condition on the valuation of z. Why is that one so important?
Well, it comes from a delicate interplay between the structure of the matrices involved and the constraints imposed by cuspidality. If the valuation of z doesn't satisfy this condition, then Rg ends up containing either u1 or u2, again leading to a contradiction.
So it's like a balancing act with cuspidality as the tightrope walker.
That's a great analogy.
Okay, so lemma 3.6 gives us a lot of very specific conditions on those double causes. What's next?
Well, next up is lemma 3.7, which offers a helpful simplification. It allows us to focus on the intersection of our double causates with the Siegel-Levi subgroup M. Remember M?
Yeah, it's the subgroup of matrices with that block structure, zeros in the bottom left, 2x2 block.
You got it. And lemma 3.7 says that if a double coset G belongs to septet, we can actually just work with the double coset NGASPM, which is basically the intersection of G with M.
Okay, so we're zooming in on a specific part of the space.
Exactly. And this simplification is really powerful because it lets us reduce the complexity of our calculations without losing any information about the dimension of the space of Siegel vectors.
That's a win-win.
Absolutely. And finally, we reached the grand finale of Section 3, Lemma 3.8.
The culmination of all our efforts.
It is. Lemma 3.8 puts all the pieces together and gives us a complete characterization of the double cosets that belong to sup. It tells us that any double coset in sup has to have one of 4 specific forms, and then it gives us the precise conditions for each of those forms to actually be in sup.
So it's like we finally identified the suspects in our mathematical whodunit.
Exactly. We know exactly what those double cosets look like, and we have all the tools we need to count them.
Okay, so we've laid all the groundwork, we've explored all the nooks and crannies of sup, and we've developed all these powerful techniques using character tables and cuspidality and conjugation and p-adic valuations. It's been quite a journey.
It has, but it's all been leading up to this. We're now ready to calculate those dimensions and uncover the secrets of those Siegel vectors.
I can't wait. And to our listeners, thank you for joining us on this incredible deep dive into the world of representation theory. We've covered a lot of ground, but we hope you've enjoyed the ride.
And if this has sparked your curiosity, remember, this is just the tip of the iceberg. There's so much more to explore in this fascinating field.
So keep those mathematical minds engaged, and we'll see you on our next deep dive.